Some places seem impossible for a simple reason: they should not have survived. Empires disappeared, kingdoms collapsed. Wars, earthquakes, floods, and changing climates reshape the world again and again. Yet scattered across the planet are ancient structures that endured through all of it. They've watched civilizations rise around them and vanish beneath them. They've outlived the languages spoken within their walls and the people who once understood every detail of their design. Today, we can still touch the same stone, follow the same corridors, and stand in the same spaces. But one thing remains beyond our reach: certainty. Because surviving is not the same as being understood. And some of the world's oldest monuments continue to prove that the hardest part of history is not preserving the evidence. It is understanding what the evidence truly means. The eastern Nile delta of Avaris hid the remains of a city that should not have existed at that level of technological complexity over 3,500 years ago. Massive harbour systems, advanced furnaces, engineered foundations, and international trade networks appeared in a place historians once believed was little more than swampy floodplain. Yet Avaris may have been one of the most technologically advanced cities of the Bronze Age. The ruins of Avaris were gradually identified during excavations at Tel el-Dabar in the 1960s, led by Austrian archaeologist Manfred Biertak. What initially looked like scattered mud brick settlements soon revealed enormous harbour basins, palace districts, workshops, warehouses, and foreign-style architecture buried beneath meters of Nile sediment. Ground-penetrating surveys later showed that much of the city had been hidden under shifting river channels for millennia. Radiocarbon dating places the peak of Avaris between roughly 1700 and 1550 BCE, during the rule of the Hyksos, a foreign dynasty that controlled northern Egypt. Ancient texts describe the Hyksos as outsiders, but archaeology began showing something far more disturbing. They may also have introduced engineering systems and industrial technologies far ahead of their time. One of the greatest mysteries of Avaris is its gigantic harbour network. Excavations revealed artificial basins and canals connected directly to branches of the Nile. Some harbour areas stretched hundreds of meters wide, large enough to accommodate major cargo traffic during the Bronze Age. What shocked researchers was the precision of the hydraulic planning. Sediment analysis showed controlled water flow patterns instead of random flooding. Canal depths remained surprisingly uniform despite being dug into unstable delta soil. Maintaining navigable waterways in the Nile Delta would have required constant dredging, water management, and advanced surveying knowledge. Modern geoarchaeologists compared parts of Avaris' water system to later Phoenician and even Roman port engineering. Yet Avaris predates many of those systems by more than 1,000 years. The Nile Delta was one of the most unstable landscapes in the ancient world. River branches shifted constantly, floods reshaped the terrain every year, and soft alluvial mud could collapse engineered structures quickly. Despite this, Avaris operated as a large international port for generations. Some archaeologists believe the Hyksos may have used detailed observational hydrology, studying sediment movement, flood timing, and seasonal current changes with a sophistication never fully documented in surviving Egyptian records. The city's buildings present another unexplained engineering puzzle. Large structures in Avaris were built on waterlogged delta ground that should have been incapable of supporting heavy architecture for long periods. Yet many buildings survived for centuries. Excavations found layered sand beds, compacted mud brick platforms, reedment reinforcement, and organic stabilization materials beneath foundations. This resembles primitive soil distribution engineering, similar in principle to modern floating foundations used in unstable environments. In some districts, archaeologists discovered alternating layers of clay and sand beneath palace floors, likely designed to absorb movement caused by moisture shifts and subsidence. These methods reduce structural stress in terrain where ordinary mud brick cities should have cracked apart rapidly. Comparable stabilization systems would later appear in Mesopotamian marsh settlements and much later in parts of Venice. But Avaris demonstrates these ideas appearing extraordinarily early. Researchers still debate whether these systems evolved locally or were imported from engineering traditions outside Egypt. The most controversial discoveries at Avaris involve metallurgy. Excavations uncovered large industrial zones filled with furnaces, copper slag, molds, crucibles, tuyères, and evidence of large-scale bronze production. Some furnaces show thermal damage suggesting temperatures exceeded 1,100 degrees Celsius, high enough for sophisticated bronze alloy processing. For comparison, ordinary open Bronze Age fires rarely sustain such temperatures efficiently without advanced airflow control. The furnaces at Avaris appear to have been engineered to maximize oxygen intake through carefully angled air channels. Some researchers believe they used forced draft systems, powered either by bellows or by exploiting prevailing Nile Delta winds. The internal furnace geometry may have created natural pressure acceleration, similar to primitive blast furnace principles. This is where their mystery deepens. Several slag samples indicate remarkably consistent alloy composition. That implies controlled metallurgical processes rather than random heating. Certain bronze artifacts contain balanced tin percentages that improved hardness while preventing brittleness, knowledge requiring repeated experimentation and careful thermal control. Archaeometallurgists have compared some manufacturing precision at Avaris to later Late Bronze Age industrial centres in Anatolia and Cyprus. Yet Avaris reached this level surprisingly early. Fuel consumption also raises questions. Producing temperatures above 1,100 degrees Celsius in large numbers of furnaces should have required enormous quantities of charcoal. However, evidence for equally massive nearby deforestation remains limited. Some researchers speculate the furnace systems were unusually fuel-efficient due to airflow optimization. Even more puzzling are traces of arsenical copper production found in some areas. Arsenic bronze can produce harder tools than pure copper, but the process releases toxic fumes. Long-term production would have been extremely dangerous without some understanding of ventilation. Yet many workshop zones in Avaris were positioned to exploit dominant wind directions across the delta. Whether intentional or accidental remains unknown. Some scientists now believe Avaris functioned as one of the largest metallurgical centers in the Eastern Mediterranean during its time, a scale of industrial organization historians once thought impossible for the period. Inside elite buildings at Avaris, archaeologists discovered fragments of wall paintings unlike traditional Egyptian art. The style matched Minoan frescoes from Crete almost perfectly. Bull-leaping scenes, flowing marine imagery, layered pigments and plaster techniques all resembled artwork from Knossos over 700 kilometers away across the Mediterranean. The implications were enormous. This suggested that Avaris was connected to an international maritime trade network far larger than historians previously imagined. Some experts even proposed that Minoan artists may have physically traveled to Egypt. Pigment analysis showed imported minerals and sophisticated multi-layer painting methods requiring controlled plaster timing before drying. The techniques were highly specialized and difficult to reproduce without trained artisans. The discovery transformed Avaris from a regional Egyptian city into evidence of a deeply interconnected Bronze Age world system. Another mystery lies inside the storage complexes. Many warehouse structures appear to contain passive cooling and ventilation systems. Narrow airflow corridors, double-wall construction, elevated floors, and carefully oriented openings reduced humidity and heat build-up naturally. Experimental archaeology suggests some storage chambers may have remained several degrees cooler than outside temperatures even during hot Nile summers. For a city dependent on grain, oils, timber, copper, and imported goods, climate-controlled storage would have been essential. Moisture alone could destroy massive food reserves in the delta environment. Some engineers compare these passive systems to principles later seen in Persian wind catchers and Roman storage engineering. Again, Avaris seems to demonstrate technological solutions appearing centuries before historians expected. Avaris once served as a major center of chariot technology and military logistics in ancient Egypt. Before the Hyksos period, horses were almost unknown in Egyptian warfare, yet excavations at the site uncovered stables, chariot components, and large-scale supply infrastructure. The Hyksos are believed to have introduced composite bows and horse-drawn chariots into Egypt, permanently transforming Bronze Age warfare. Some stable areas even featured advanced drainage and ventilation systems, suggesting Avaris may have supported hundreds of horses at once, a level of logistical organization far beyond most Bronze Age cities. Do you think Avaris was simply an advanced Bronze Age city, or evidence that ancient civilizations understood engineering far beyond what history tells us? Share your thoughts in the comments below. Heraclea at Latmus sits beside Lake Bafar in western Turkey, surrounded by colossal granite mountains that look almost artificial. Here, massive defensive walls climb impossible slopes, prehistoric rock paintings cover remote cliffs, and ancient water systems still survive after more than 2,000 years. Archaeologists still cannot fully explain how a city built on terrain this hostile managed to engineer stone fortifications, waterproof reservoirs, and complex infrastructure that rivaled far larger civilizations. The ruins of Heraclea at Latmus became widely studied during 19th century European archaeological surveys across Anatolia. Early explorers were shocked by the scale of the fortifications hidden among the granite formations of the Latmus Mountains. Later excavations revealed something even stranger. The region was not occupied by only one civilization. Around the city, researchers discovered prehistoric rock paintings dating back nearly 8,000 years, centuries before classical Greek settlement ever appeared there. Scientific analysis later showed that Heraclea originally stood close to the Aegean coastline. Over thousands of years, sediment carried by the Buyuk-Menderes River slowly pushed the sea away, transforming the harbour into marshland and eventually into the modern Lake Bafar region. This meant the city survived dramatic environmental changes that would have destroyed many ancient settlements dependent on maritime trade. The first major mystery of Heraclea is its location itself. Most ancient Greek cities were built on relatively manageable terrain, where transportation and construction were practical. Heraclea ignored that logic completely. The city was constructed directly among enormous granite boulders, many rising over 20 meters high, with steep inclines and unstable surfaces that remain difficult even for modern climbers. Despite this, the inhabitants built defensive walls stretching roughly 6.5 kilometers. Some sections still stand over 10 meters tall. The stones used in the fortifications weigh several tons each, yet many were fitted together with extraordinary precision. Archaeologists have compared portions of the masonry to the polygonal stonework found at Mycenae and even certain defensive sectors of Pergamon. However, Heraclea's terrain is significantly harsher. The engineering challenge becomes even more difficult when considering transportation. Ancient builders would have needed to move heavy stone blocks uphill through fractured granite landscapes without advanced machinery. Researchers estimate that some blocks required coordinated labor forces of dozens of workers. Yet there is little evidence of the wide transport roads usually associated with large-scale ancient construction projects. Some historians believe the builders used the mountain itself as part of the architecture rather than attempting to reshape it. Walls were often connected directly into natural rock formations, creating a hybrid defensive system between natural geology and human engineering. This technique resembles certain Andean fortifications in Peru more than traditional Greek urban planning. Heraclea's defensive system was not simply large, it was strategically sophisticated in ways that continue to surprise military historians. Watchtowers were positioned to maximize visibility across narrow mountain corridors and lake approaches. Instead of relying on flat defensive perimeters, the builders created overlapping observation zones using elevation differences and natural rock barriers. Modern analysts sometimes describe this as an early form of terrain-optimized warfare engineering. Certain tower positions allowed defenders to monitor enormous areas while remaining extremely difficult to attack directly. Similar principles would later appear in Byzantine mountain fortresses nearly 1,000 years afterward. Even more unusual is the way some walls curve around granite formations instead of cutting through them. This reduced construction effort while also increasing defensive unpredictability. Invading forces could not easily anticipate blind corners or elevated ambush positions. The landscape itself became part of the weapon system. The greatest technological mystery of Heraclea may not be its walls, but its survival systems. Water management in mountainous terrain is extraordinarily difficult. Seasonal droughts, shifting shoreline conditions, and unstable runoff patterns would have constantly threatened the city's population. Yet archaeological surveys uncovered an extensive network of cisterns, channels, carved reservoirs, and stone-cut storage systems integrated directly into the mountain. Some reservoirs were carved into granite itself and coated with waterproof materials that still remain partially functional today. This is one of the most debated aspects of the site. Granite is notoriously difficult to seal because microscopic fractures allow slow water leakage over time. Yet certain Heraclea reservoirs retained structural integrity for more than 2 millennia despite earthquakes, climate changes, and erosion. Researchers studying the remaining plaster layers found evidence of mineral-based waterproof compounds, possibly containing lime mixtures, volcanic additives, and finely processed aggregates similar to Roman hydraulic concrete. The comparison with Roman engineering is important because many Roman waterproof systems relied on pozzolanic ash mixtures, capable of chemically reacting with water to strengthen over time. However, Heraclea's systems appear adapted specifically for mountainous granite environments rather than coastal harbour construction. Some channels were designed to redirect runoff during heavy seasonal rains, preventing sudden flooding from destroying the city's infrastructure. Others appear connected to long-term storage systems that could preserve water through dry periods. This level of environmental adaptation suggests advanced hydrological understanding, far beyond what most people associate with smaller Hellenistic settlements. Researchers have also noted similarities between Heraclea's water systems and ancient Persian water management traditions such as qanat engineering, where water pressure, slope control, and underground distribution were carefully calculated. Whether these similarities emerged independently or through cultural exchange remains uncertain. Perhaps the strangest detail is durability. Certain waterproof coatings survived far longer than many medieval mortars exposed to similar conditions. Some experts believe the builders may have discovered local mineral combinations uniquely suited for granite adhesion. If true, it would mean Heraclea possessed regional engineering knowledge that was highly specialized and later lost. Long before Heraclea became a Greek city, the Latmus Mountains were already sacred. Hundreds of prehistoric rock paintings discovered across the region date back roughly 8,000 years to the Neolithic era. Unlike many prehistoric sites dominated by hunting imagery, Latmus paintings frequently depict groups of humans standing together, ritual gatherings, geometric symbols, and unusual paired figures. This has led some archaeologists to propose that the mountains served ceremonial or cosmological purposes rather than purely survival-based activities. Several rock formations in the region naturally align with sunrise positions during specific times of the year. Narrow gaps between granite towers create framed solar viewing points, resembling primitive observation corridors. Although no definitive astronomical observatory has been confirmed, researchers continue investigating whether the area functioned as an early ritual landscape connected to seasonal cycles. Comparisons are often made to sites such as Chaco Culture National Historical Park and Nabta Playa, where prehistoric communities appear to have integrated landscape geometry with celestial observation. The Temple of Athena at Heraclea contains another unresolved puzzle. Some granite foundation stones display cutting marks with surprisingly straight channels and smooth surfaces. Granite ranks among the hardest natural building stones, and shaping it requires enormous effort even with iron tools. Yet several blocks appear cut with a consistency difficult to explain through primitive hammering methods alone. Similar debates exist at Baalbek, Ollantaytambo, and parts of ancient Egyptian stonework. Mainstream Astuta archaeology attributes such precision to long-term labor, abrasion techniques, and advanced craftsmanship rather than lost high technology. Still, Heraclea adds another example to the growing list of ancient sites where stone engineering appears more sophisticated than expected for the era. Another lesser-known mystery involves sound. Certain granite corridors and cavities within the Latmus Mountains produce unusually long echoes and resonance effects during strong winds or loud noises. Some researchers suspect these acoustic zones may have influenced ritual activity in the region for thousands of years. Natural amphitheatre-like formations can amplify voices across surprising distances without artificial construction. In a landscape already associated with ritual paintings and sacred symbolism, these acoustic effects may not have gone unnoticed by ancient inhabitants. Modern acoustic mapping in rocky archaeological environments has shown that many ancient ceremonial sites were intentionally selected for their sound properties. Whether Heraclea's surrounding mountains were chosen partly for this reason remains an open question. More than 3,000 meters above sea level in the highlands of Apurímac, Peru, the ruins of Sondor rise across a mountain ridge, like the remains of a civilization that should not have possessed this level of engineering. Massive stone terraces cut directly into steep Andes slopes. Flattened ceremonial platforms stand balanced on unstable mountain terrain. Drainage systems still function after centuries of earthquakes and erosion. Almost no written records survive from the people who built it. Yet Sondor may preserve evidence that the Chanka civilization understood large-scale mountain engineering far better than historians once believed. The site was identified through archaeological surveys in the 20th century, although local communities had known of the ruins for generations. Excavations revealed ceremonial plazas, defensive structures, stair systems, canals, and a massive stepped ceremonial platform known as an usnu. Researchers quickly realized Sondor was not a random hill settlement. It had been carefully designed around the mountain itself, transforming dangerous terrain into an organized ceremonial and political center. What shocked archaeologists was not only the scale of the construction, but the precision achieved at an altitude where even modern engineering projects face severe logistical problems. The greatest mystery surrounding Sondor is the enormous mountain flattening system that still lacks a complete explanation. Much of the complex sits on steep volcanic slopes where natural construction would normally be impossible. Modern engineers understand that leveling terrain on mountains is one of the hardest forms of large-scale construction, because gravity constantly destabilizes the ground beneath the structure. Landslides, water erosion, seismic movement, and uneven load distribution can destroy foundations over time. Yet the builders of Sondor somehow carved enormous ceremonial platforms directly into the mountainside while maintaining long-term structural stability. Some terraces at Sondor extend across sharply inclined terrain with surprisingly uniform horizontal alignment. To create these surfaces, ancient workers would have needed to remove thousands of tons of rock and soil without steel tools, explosives, or wheeled transport. Archaeologists estimate that even small-scale terracing projects in the Andes required massive organized labor forces. At Sondor, the complexity goes beyond agriculture. These were ceremonial and political platforms requiring exact geometric leveling. The problem becomes even more astonishing considering the elevation. At over 3,000 meters, oxygen levels drop significantly compared to sea level, reducing physical work efficiency. Modern physiological studies show that oxygen availability at these elevations can fall by roughly 30%, making heavy labor dramatically harder. What makes Sondor unusual compared to other Andes sites is the apparent understanding of slope stabilization. In modern mountain engineering, retaining walls must redirect pressure laterally to prevent collapse. Many structures at Sondor appear to follow similar principles. Stone retaining systems absorb mountain pressure while allowing water to escape through drainage gaps. This reduces hydrostatic buildup, one of the primary causes of wall failure in mountainous environments. Similar concepts exist in later Inca sites such as Machu Picchu, where underground drainage systems account for nearly 60% of the site's engineering infrastructure. But Sondor may predate some of the most famous Inca hydraulic solutions, raising uncomfortable questions about where this knowledge originally emerged. The Chanca civilization itself remains poorly understood. Most surviving information about them comes from Inca chronicles written after violent wars between the two cultures in the 15th century. According to those records, the Chanca were feared military rivals capable of threatening Cusco before the rise of Emperor Pachacuti. But Sondor suggests they were far more than warriors. The engineering complexity of the site points to organized architectural planning, labor administration, geological understanding, and possibly even mathematical surveying techniques. One of the strangest aspects of Sondor is how precisely its structures interact with the natural topography. Instead of forcing straight-line geometry onto the landscape, many walls adapt organically to the mountain's contours. This reduces stress concentrations during earthquakes. Modern earthquake engineering often relies on distributing force across irregular structures rather than rigid, symmetrical systems. Some researchers believe ancient Andes builders discovered similar principles through centuries of experimentation in one of the most seismically active regions on Earth. Peru experiences thousands of detectable earthquakes every year due to tectonic interaction between the Nazca Plate and South American Plate. Yet portions of Sondor remain standing after centuries of seismic activity. The stonework itself creates another unanswered puzzle. While not as refined as the famous polygonal masonry of Cusco, many blocks at Sondor were still shaped with remarkable precision. The stones interlock closely enough to reduce instability without requiring mortar. Historians still debate exactly how ancient Andes civilizations achieved this level of shaping. Experimental archaeology has shown that hammerstones and abrasion techniques can produce smooth surfaces, but reproducing large-scale precision fitting remains extremely time-consuming, even under controlled conditions. At Sondor, workers perform this process while transporting materials across steep mountain terrain with no draft animals capable of carrying massive stone loads. Water management may be the clearest sign of advanced engineering at the site. Mountain environments create violent seasonal runoff capable of destroying foundations within decades. Yet Sondor includes channels and runoff systems specifically designed to redirect rainwater away from ceremonial sectors. Some drainage paths appear integrated directly into terrace architecture. Modern civil engineers recognize that improper water management causes more structural failures in mountain settlements than earthquakes themselves. Without drainage control, soil saturation weakens foundations and triggers slope collapse. The survival of Sondor suggests its builders deeply understood how water behaves under mountain pressure. At the center of the complex stands the giant Usnu platform, perhaps the most mysterious structure in the entire site. Elevated above surrounding sectors, it dominates the ridge with a commanding panoramic view across valleys and distant peaks. Similar Usnu structures throughout the Andes are associated with ritual ceremonies, political authority, and astronomical observation. At Sondor, some researchers suspect the platform may have been aligned with solar events or seasonal cycles tied to agriculture and religious ceremonies. Certain stairways and sightlines appear oriented towards specific mountain horizons where the sun rises during important points of the year. While evidence remains inconclusive, the possibility connects Sondor to a broader Andes tradition of integrating astronomy directly into architecture. Comparisons with other ancient civilizations make the mystery even deeper. Across the ancient world, societies that mastered mountain engineering often possessed centralized bureaucracies and advanced logistical systems. The Romans used concrete and complex surveying instruments to stabilize mountain roads and aqueducts. The Nabateans at Petra carved hydraulic systems into desert cliffs using sophisticated water calculations. The Inca developed road systems stretching over 40,000 kilometers across impossible terrain. But the Chanca left behind little written evidence, explaining how they organized projects like Sondor. That absence creates one of archaeology's most frustrating gaps. The engineering survived. The explanations did not. Perhaps the most unsettling possibility is that Sondor represents only a fragment of a much larger lost technological tradition in the Andes. Many historians once treated pre-Inca civilizations as culturally fragmented societies lacking unified engineering sophistication. But discoveries across Peru continue to challenge that assumption. Advanced terracing hydraulic systems, seismic-resistant masonry, and astronomical architecture appear repeatedly across different cultures separated by centuries. This suggests knowledge was transmitted, refined, and inherited long before the Inca Empire emerged. What do you think the builders of Sondor truly understood about mountain engineering that history has forgotten? Share your theory in the comments below. Northern Egypt, deep within the Nile Delta, hides the remains of Buto, a settlement older than the pyramids, buried beneath layers of mud and groundwater for over 5,000 years. What archaeologists uncovered there was not just an ancient town, but evidence of engineering, ceramic technology, and trade systems that seem impossibly advanced for prehistoric Egypt. Buto remained largely invisible for centuries because much of the site was submerged beneath Nile sediment and marshland. Modern excavations intensified during the late 20th century through German archaeological missions, led by the German Archaeological Institute. Beneath meters of alluvial mud, researchers uncovered layers dating back to around 4000–3000 BCE during Egypt's pre-dynastic period. What shocked archaeologists was the technological complexity buried within those layers. Instead of primitive village remains, they found evidence of specialized production, long-distance trade, controlled firing technology, and surprisingly sophisticated urban planning. The greatest mystery surrounding Buto is its ceramic technology. Thousands of pottery fragments discovered at the site reveal levels of heat control that should have been extremely difficult for such an early civilization. Laboratory analysis of several ceramic samples suggests firing temperatures may have exceeded 900 degrees Celsius, with some researchers proposing temperatures approaching 1000 degrees Celsius in specific kiln conditions. For comparison, ordinary open fire pottery from many Neolithic cultures rarely exceeded 600–700 degrees Celsius, because temperature fluctuations caused cracking and uneven mineral transformation. Yet Buto ceramics display unusually consistent coloration, dense internal structures, and reduced porosity, signs of controlled oxygen flow and sustained high heat. Even more puzzling is the appearance of early glazed or semi-glazed surfaces resembling primitive faience technology. Producing such finishes requires careful balancing of silica, alkali compounds, and temperature stability. In later Egyptian history, faience production became one of the civilization's most sophisticated chemical crafts. But at Buto, traces of these techniques appear centuries earlier than expected. Archaeologists also discovered evidence suggesting compartmentalized kiln systems rather than simple pit firing. Some ceramic fragments show nearly identical thermal exposure patterns, implying the heat inside the kiln was distributed evenly. Achieving that requires airflow management, insulation control, and fuel regulation, concepts associated with far later industrial pottery traditions. This has led researchers to compare Buto with ancient technological centers like Mehrgar and Çatalhöyük, where surprisingly advanced firing technologies also emerged long before large-scale states existed. In all three cases, archaeologists face the same question. How did prehistoric societies develop such precise thermal engineering without leaving behind transitional stages of experimentation? Some theories suggest Buto's artisans inherited forgotten knowledge from earlier Nile Delta cultures now lost beneath sediment and rising groundwater. Others believe the region may have functioned as an independent technological hub, connected to wider Near Eastern innovation networks thousands of years before formal empires emerged. Another major mystery involves the enormous trade system connected to Buto. Excavations uncovered obsidian blades whose volcanic composition points toward Ethiopia or Anatolia, copper originating from Sinai, and exotic stones unavailable anywhere in the Nile Delta. Transporting these materials across distances exceeding 1,000 kilometers during the 4th millennium BCE should have been extraordinarily difficult. Yet the volume of imported material found at Buto suggests this was not occasional exchange. It was organized commerce. This challenges older theories that pre-dynastic Egypt was composed mainly of isolated agricultural villages. Instead, Buto may have operated as a strategic trade hub linking the Mediterranean coast, the Levant, Upper Egypt, and Eastern Africa. Its location within the Nile Delta likely played a major role. At the time, the delta was not a stable landscape, but a shifting maze of marshes, lagoons, distributaries, and seasonal waterways. Navigating it required detailed environmental knowledge. Some archaeologists believe the inhabitants of Buto may have possessed advanced water navigation systems and seasonal mapping traditions long before formal cartography existed. Comparisons are often made with Mohenjo-Daro, where river-based commerce also supported surprisingly large urban networks during the Bronze Age. But Buto predates many of these systems, making its logistical sophistication even more difficult to explain. Perhaps one of the least discussed but most fascinating mysteries is how Buto survived at all. The settlement was constructed on soft Nile Delta soil, an environment highly vulnerable to subsidence, flooding, and structural collapse. Yet excavations show multiple occupation layers stacked over centuries without catastrophic destruction. Soil analysis indicates inhabitants may have intentionally stabilized foundations using compressed clay, gravel mixtures, and organic reinforcement layers. Some archaeologists compare this to primitive geotechnical engineering. The concept is astonishing because similar foundation stabilization methods are better known from much later civilizations such as Mesopotamia or Rome. In modern engineering, wetland construction requires load distribution and drainage control to prevent sinking. Somehow, Buto's builders appear to have developed basic versions of those principles over 5,000 years ago. Certain elevated sectors of the settlement also suggest deliberate landscape modification. Researchers suspect the inhabitants created artificial raised platforms to protect key structures from seasonal flooding. If confirmed, Buto would represent one of the earliest known examples of large-scale environmental engineering in Egyptian history. The artifacts discovered at Buto reveal another unresolved mystery: astonishing precision craftsmanship. Small stone beads excavated at the site contain drilled holes only a few millimeters wide, yet remarkably straight and symmetrical. Creating such perforations in hard stone with pre-dynastic technology remains controversial. Experimental archaeologists have attempted to replicate these holes using reed drills, sand abrasives, and copper tools, but reproducing the same consistency is extremely time-consuming. Several engraved ceremonial objects also display microscopic linework difficult to achieve with primitive cutting instruments. Some researchers argue this indicates the existence of specialized copper tools far earlier than traditionally believed. Comparable craftsmanship has been documented at Nakada and even in Indus Valley sites, suggesting that highly specialized artisan classes may have emerged much earlier in human civilization than once assumed. Buto's survival depended entirely on controlling water. The Nile Delta constantly shifted through flooding, erosion, and marsh expansion. Entire settlements could disappear within decades if drainage failed. Yet Buto remained continuously occupied for centuries. Archaeological surveys suggest the settlement may have included canals, drainage paths, levees, or artificially elevated zones designed to redirect floodwater. This possibility has enormous implications. Large-scale hydraulic management is usually associated with dynastic Egypt and centralized pharaonic authority, but Buto may prove that complex environmental control systems existed long before the first pharaoh unified Egypt. Some researchers even believe the delta populations developed unique ecological engineering techniques adapted specifically for marsh survival. Knowledge later absorbed into early Egyptian state infrastructure. Do you think Buto was simply an advanced settlement for its time, or evidence of a lost technological culture far older than we realize? Share your thoughts in the comments below. Anamurium sits on the southern coast of Turkey, facing the open Mediterranean where salt, earthquakes, humidity, and pirate raids should have erased an ancient city long ago. But Anamurium refused to disappear. Beneath collapsing arches and silent bathhouses lies evidence of engineering, materials, and chemical knowledge that still challenge archaeologists today. The ruins were first systematically documented in the 19th century, but major excavations accelerated during the 1960s under Canadian archaeologist Elizabeth Rosenbaum. What researchers uncovered was not just another Roman coastal settlement. They found one of the best preserved necropolises in Anatolia, sophisticated water systems, unusually durable building materials, and mosaics whose colours survived nearly 2 millennia of Mediterranean sunlight and sea air. The deeper excavations went, the stranger the city became. One of the first mysteries involves survival itself. Anamurium stands directly beside the sea in a region exposed to constant humidity and salt-laden winds. Modern reinforced concrete near coastlines can begin deteriorating within decades as chloride ions penetrate the material and corrode internal structures. Yet many of Anamurium's walls, cisterns, and bath complexes remain structurally stable after nearly 1,700 years. Some Roman maritime concrete structures in Italy, such as those at Pozzuoli, are known to strengthen over time through chemical reactions involving volcanic ash and seawater. but Anamurium is hundreds of kilometers away from the major volcanic zones traditionally associated with that technology. Material analysis from comparable Roman coastal sites suggests builders may have used hydraulic lime mixtures containing pozzolanic compounds capable of forming rare minerals like aluminum tobermorite. These crystals increase resistance against cracking and chemical erosion. The mystery is logistical as much as chemical. If similar materials were used at Anamurium, where did they come from? Transporting specialized mineral additives across the Mediterranean would have required a remarkably organized maritime supply network at a scale historians once underestimated. The city's water system creates another puzzle. Southern Anatolia experiences long dry summers, yet Anamurium supported bathhouses, fountains, storage reservoirs, and a large urban population for centuries. Archaeologists mapped aqueduct gradients that remained astonishingly precise across uneven rocky terrain. In some sections, the slope variation is so minimal that even small errors would have stopped water flow or created destructive pressure surges. Modern gravity-fed water systems often rely on laser measurement tools to maintain similar consistency. Roman surveyors supposedly worked using simple instruments like the chorobates and groma, yet the hydraulic precision seen here rivals far later engineering systems. The mystery becomes more striking when compared to medieval Europe. In many medieval cities over 1,000 years later, sewage and water control systems remained primitive and inconsistent. Yet at Anamurium, centuries earlier, engineers maintained controlled water distribution in one of the Mediterranean's harshest coastal environments. This raises a disturbing possibility. Certain branches of practical engineering knowledge may have been partially lost after the collapse of the Roman world. The bathhouses reveal another unexplained achievement. Anamurium used hypercaust heating systems in which hot air circulated beneath raised floors and through wall cavities. Normally, coastal moisture and thermal expansion gradually destabilize these hollow floor systems. Modern concrete structures exposed to repeated thermal cycling often develop microfractures within decades. Yet portions of Anamurium's heated floors survived for over a millennium. Some structural engineers believe Roman builders may have unintentionally created early forms of flexible composite construction. Their mortar mixtures sometimes contain crushed ceramics, volcanic particles, lime, and varying aggregate sizes that distributed stress more efficiently than rigid modern cement. Ironically, some modern Portland cement structures degrade faster because they are too rigid under environmental stress. In certain ways, Roman materials behaved less like brittle stone and more like adaptive geological systems. Then there is the necropolis, one of the largest surviving Roman cemeteries in Anatolia. Hundreds of tombs spread across unstable coastal terrain vulnerable to erosion and seismic activity. Yet many remain standing despite centuries of earthquakes affecting the eastern Mediterranean. Geological studies suggest some structures distributed weight unusually well across softer soil layers instead of anchoring deeply into rigid foundations. Modern earthquake-resistant architecture often relies on controlled flexibility rather than absolute rigidity. Japanese seismic engineering, for example, allows buildings to absorb and redistribute movement rather than resisting it completely. The unsettling question is whether ancient builders discovered similar principles empirically through generations of observation. If so, Anamurium may preserve evidence of forgotten seismic adaptation techniques developed nearly 2,000 years before modern structural dynamics emerged as a scientific discipline. But perhaps the strangest mystery of all appears inside the city's surviving mosaics and pigments. At first glance, the mosaics seem merely decorative. Geometric floors, coloured stone patterns, fragments of wall paintings. But laboratory examinations reveal something deeply unusual about their durability. The Mediterranean climate is brutally destructive to pigments. Ultraviolet radiation breaks molecular bonds. Salt crystallization fractures surfaces internally. Humidity accelerates chemical reactions that bleach ancient colours. Even many medieval frescoes deteriorated rapidly under such conditions. Yet some pigments at an inert murium retained remarkable chromatic stability after nearly 2,000 years. Researchers studying Roman pigments across the Mediterranean identified compounds containing iron oxides, Egyptian blue, cinnabar, carbon black, and copper-based minerals capable of resisting extreme environmental degradation. Egyptian blue is especially mysterious. First synthesized over 4,500 years ago, it is considered humanity's earliest synthetic pigment. Modern scientists discovered that it emits infrared luminescence invisible to the human eye, a property now being explored for anti-counterfeit technologies and advanced imaging systems. What makes this disturbing is not merely that ancient civilizations created durable pigments. It is that some of these manufacturing methods remain incompletely understood even today. Reproducing exact ancient pigment compositions consistently has proven difficult because tiny variations in temperature, mineral purity, kiln atmosphere, and particle size dramatically affect the final chemical stability. At Anamurium, several mosaic fragments survived conditions that should have erased them centuries ago. In some protected areas, pigment adhesion remained unusually strong despite prolonged salt exposure. Certain mineral combinations appear to have formed microscopically stable crystalline bonds with plaster surfaces, reducing flaking and moisture penetration. In modern conservation science, researchers still struggle to develop restoration materials capable of matching the longevity of some Roman pigments. The comparison becomes even more uncomfortable when viewed against modern architecture. Many contemporary paints begin fading within years under ultraviolet exposure. Some modern coastal concrete structures require major restoration after only 50 to 100 years. Meanwhile, ancient pigments at Anamurium endured nearly 20 centuries of sea air, storms and heat, while preserving visible colour integrity. This pattern appears repeatedly across the ancient world. Roman concrete outlasting modern seawalls. Egyptian pigments resisting ultraviolet decay longer than industrial paints. Ancient hydraulic systems maintaining stable gradients without electronic instruments. Again and again, archaeology uncovers technologies that seem primitive according to historical narratives, yet perform at levels surprisingly difficult to replicate. Do you think civilizations like Anamurium truly possessed engineering knowledge far beyond what history tells us? Or are modern scientists still underestimating the capabilities of the ancient world? Share your thoughts in the comments below. Rising above the Rhodope Mountains of southern Bulgaria near the modern town of Asenovgrad is a massive stone plateau more than 1,200 meters above sea level. From the air, it looks almost unnatural. A giant slab of exposed granite carved with channels, pits, basins, geometric cuts, and strange depressions that seem too deliberate to be random geology. The site is known as Belintash Plateau, and for decades it has remained one of the least understood ancient sites in Eastern Europe. Unlike famous megalithic locations such as Stonehenge or Machu Picchu, Belintash receives little international attention. Yet many archaeologists and geologists agree that some of its features are extremely difficult to explain using conventional Bronze Age technology. The discovery of Belintash as a serious archaeological site began relatively late. Although local legends about the plateau existed for centuries, systematic studies only intensified during the 20th century when Bulgarian archaeologists noticed unusual patterns carved directly into the granite surface. Excavations revealed ceramic fragments, ritual remains, and evidence connected to the ancient Thracians, a civilization that occupied large parts of the Balkans more than 3,000 years ago. But the deeper researchers looked, the stranger the plateau became. The first major mystery is the stone processing itself. Belintash is composed primarily of granite, one of the hardest natural construction materials commonly encountered by ancient civilizations. Granite measures around 6 to 7 on the Mohs hardness scale, meaning it is harder than bronze and difficult even for iron tools to shape efficiently. Yet across the plateau are dozens of straight channels, flattened surfaces, drilled depressions, and sharply defined cuts extending across large sections of exposed rock. Some grooves maintain surprisingly consistent depth over long distances, while others intersect at angles that appear intentionally geometric rather than natural. This becomes difficult to explain when compared to known Bronze Age stoneworking methods. Ancient Egyptians, for example, processed granite extensively at Aswan and inside pyramids, but they left clear chisel marks, pounding traces, and visible tool damage. Even with enormous labour forces, shaping granite was incredibly slow. Experimental archaeology suggests that smoothing 1 square metre of granite using primitive hammerstones can require dozens of labour hours. At Belintash, however, flattened areas extend across tens of square metres. If all of this work was done manually, the labour investment would have been enormous for a mountain sanctuary occupied by a relatively small population. Some researchers argue that many of the formations could be natural erosion, but this explanation struggles to account for the repeated linear patterns and the organisation of several channels. During heavy rain, water flows through the carved grooves in highly controlled ways, almost like a primitive hydraulic system. Certain basins fill sequentially, while others drain through narrow cut paths. This has led to theories that Belintash may have functioned not only as a ritual centre, but also as a type of ceremonial water management system. That possibility is significant because advanced hydraulic engineering is usually associated with civilizations such as the Romans, Nabateans, or Maya. At sites like Petra, engineers created highly efficient water channels capable of sustaining entire desert cities. Belintash is far older and far smaller, yet some of its water flow features appear surprisingly intentional. Researchers have proposed that rainwater moving through the channels may have held ceremonial or astronomical importance, possibly linked to seasonal observations. Another unexplained feature is the series of small circular and oval depressions scattered across the plateau. Some are isolated, while others appear grouped into patterns. Local theories often describe them as star maps, suggesting they may represent constellations such as Orion or the Pleiades. While many archaeologists remain skeptical of astronomical interpretations, the geometric arrangement of certain groups continues to raise questions. Some depressions appear too regular to be random weathering, and several show signs of repeated shaping or smoothing. The problem is technological. Creating uniform depressions in granite normally requires either persistent abrasion or rotational drilling methods. Yet there is little evidence that the Thracians possessed advanced drilling technology, comparable to later Roman or Hellenistic systems. Similar debates exist at other ancient sites around the world. In Peru, polygonal stonework at Sacsayhuaman displays precision that continues to challenge modern assumptions about pre-industrial engineering. At Belintash, the mystery is smaller in scale but equally frustrating because the technical evidence appears more advanced than the surrounding archaeological culture would normally suggest. One of the most controversial mysteries involves the possibility that Belintash functioned as an astronomical observatory. Several carved lines and depressions align roughly with solar positions during equinoxes and solstices. Researchers have noted that sunlight interacts with parts of the plateau differently during specific seasons, potentially creating shadow markers or illumination points. Similar systems existed in ancient cultures worldwide. At Chichen Itza, the famous pyramid of Kukulkan creates a serpent-shaped shadow during equinoxes. At Nabta Playa, stone arrangements may have tracked seasonal celestial movements more than 6,000 years ago. But Belintash presents a problem. There is no massive architectural structure, no tower, and no obvious observatory platform. Instead, the plateau itself appears to have been modified directly into an observational surface. If intentional, it would represent a highly unusual form of prehistoric astronomical engineering integrated directly into natural geology. Geologists have also identified minor magnetic anomalies in the surrounding region. These anomalies are not extreme enough to support pseudoscientific claims about energy portals, but they are scientifically interesting because ancient cultures repeatedly selected geologically unusual sites for ritual construction. Göbekli Tepe, Delphi, and several Andean ceremonial centers were all positioned near distinctive geological formations or fault zones. Some scientists believe ancient societies may have been unusually sensitive to environmental features such as underground water movement, magnetic variation, or acoustic resonance. Acoustics may be another overlooked mystery at Belintash. Certain parts of the plateau produce unusual sound reflections due to the flat granite surfaces and surrounding cliffs. Even small voices can echo unexpectedly in particular locations. This has led some archaeologists to speculate that rituals performed there may have intentionally incorporated acoustic effects, similar to ceremonial structures found in Malta's ancient Hypogeum, where specific frequencies resonate with unusual intensity. The survival of the carvings themselves is another unresolved question. Belintash experiences harsh mountain weather, including freezing winters, strong wind exposure, and constant water erosion. Granite slowly fractures through freeze-thaw cycles, where water enters microscopic cracks, freezes, expands, and gradually breaks apart the rock. Over thousands of years, shallow carvings should become heavily degraded. Yet many channels and depressions remain surprisingly visible today. This suggests two possibilities. Either the carvings were originally much deeper and more precise than they appear now, or parts of the plateau were maintained over very long periods by repeated human activity. Both explanations imply a level of long-term occupation and technical effort that archaeologists still struggle to fully reconstruct. Perhaps the most unsettling aspect of Belintash is not what researchers know, but what they cannot explain. The plateau contains enough evidence to confirm deliberate human modification, but not enough evidence to clearly reveal its true purpose. It may have been a Thracian sanctuary, an astronomical calendar, a ritual water system, or something combining all three. Every explanation solves one mystery while creating another. What do you think Belintash really was? An ancient observatory, a sacred ritual site, or evidence of a lost engineering knowledge far ahead of its time? Share your thoughts in the comments below. The Ores Mountains of northeastern Algeria conceal one of the strangest engineering mysteries of the ancient world. Inside Batna province, an ancient city vanished beneath desert sand for centuries before archaeologists uncovered something almost impossible for its time: a near-perfect urban grid built at the edge of the Sahara. Roads intersected with mathematical precision. Underground drainage still functioned after nearly 2,000 years, and massive stone structures survived brutal temperature swings capable of destroying modern concrete within decades. The deeper researchers studied the ruins of Timgad and the surrounding settlements, the more North Africa began to resemble not a distant Roman frontier, but a lost laboratory of ancient engineering. Timgad was founded around 100 AD under Emperor Trajan, but after centuries of abandonment, wind and sand slowly buried much of the city beneath the Sahara's edge. Major excavations began during the late 19th century when French archaeologists uncovered streets, theatres, baths, drainage systems and stone roads preserved with astonishing clarity. Nearby ruins, including Lambesis, reveal that Batna province once contained one of the most advanced infrastructure networks in Roman Africa, built in terrain that should have made large-scale urban survival extremely difficult. The greatest mystery inside Batna province is not simply that Timgad existed, but how accurately it was designed. From above, the city resembles a modern blueprint more than an ancient settlement. Its streets form a remarkably organised orthogonal grid, stretching across difficult terrain near the desert edge, while the Cardo Maximus and Decumanus Maximus intersect at almost exact right angles. Even today, many ancient cities contain visible distortions caused by erosion, terrain irregularities, or inaccurate surveying, yet Timgad displays surprisingly little deviation despite being planned nearly 2,000 years ago. What makes this difficult to explain is the technological reality of the Roman world. Engineers at the time supposedly relied on ropes, wooden rods, primitive levelling tools, and manual observation, yet the city demonstrates spatial precision comparable to principles still used in modern civil engineering. Archaeologists studying Roman surveying methods discovered that sections of Timgad maintain minimal angular error across long distances. Preserving such alignment over hundreds of meters without laser levelling or optical instruments would have required extraordinary coordination, because even small cumulative mistakes could gradually distort the entire urban grid. The mystery becomes even more disturbing underground. Beneath the streets lies a drainage and sewage network engineered with extremely subtle gradients. Modern hydraulic systems depend heavily on precise slope calculation, because channels that are too steep create erosion, while channels that are too shallow cause stagnation and waste build-up. Several underground conduits at Timgad appear to maintain gradients surprisingly close to those used in efficient gravity-fed systems today. This becomes astonishing when compared with modern infrastructure failures where small drainage miscalculations can flood entire urban districts within years. Yet parts of Timgad's underground network remain recognisable after nearly 20 centuries of desert erosion, seismic activity and violent thermal expansion. Researchers also noticed that many streets appear oriented to optimise airflow and reduce heat accumulation. This matters because Batna province experiences severe temperature variation, with summer temperatures exceeding 40 degrees Celsius, while nights in elevated desert terrain can become dramatically colder. In environments like this, urban orientation directly affects long-term survival. Some historians now believe Roman North Africa may have incorporated environmental knowledge from Berber populations familiar with desert adaptation centuries before Roman expansion. Ancient texts barely document these exchanges, leaving major gaps in understanding how climatic engineering became integrated into urban planning. The city's preservation itself created another mystery. Unlike Pompeii, which was rapidly sealed beneath volcanic ash, Timgad disappeared gradually beneath layers of sand over centuries. Ironically, the desert may have protected it. Sand-insulated pavements, walls, and underground systems from moisture fluctuation, oxidation, and human destruction. Archaeologists uncovered sectors where wheel marks remained visible in ancient stone streets. The result feels unnervingly modern. Timgad does not resemble the chaotic organic growth typical of many ancient cities. It resembles a carefully engineered machine. Not far from Timgad stood Lambesis, headquarters of the Legio III Augusta. At first glance it appears to be another Roman military fortress, but deeper analysis revealed infrastructure far more advanced than expected for a semi-arid mountain environment. The fortress operated in terrain where sustaining thousands of soldiers should have been extraordinarily difficult, yet the site contained baths, workshops, sanitation systems, roads, storage facilities, and stable access to water. Maintaining such a complex required massive logistical organisation. Estimates suggest a Roman legion could consume hundreds of thousands of litres of water every week when accounting for drinking, bathing, cooking, animals, and industrial activity. Supplying that amount in harsh desert terrain without pumps or mechanised transport would have demanded exceptional hydraulic planning. The engineering mystery grows larger when examining the construction itself. Several stone blocks transported into the region weighed multiple tons, yet the surrounding terrain contains no major river systems capable of simplifying transport. Moving such material through mountainous landscapes without cranes, engines, or steel machinery remains controversial even among modern reconstruction engineers. Roman records mention rollers, pulleys, sledges, and manpower, but many researchers argue these explanations fail to fully account for the efficiency and scale visible across North African infrastructure projects. Some historians suspect forgotten regional transport methods may have been adopted from indigenous populations experienced in mountain logistics, while others believe Roman engineering capabilities were simply far more advanced than surviving texts suggest. Either explanation creates the same uncomfortable possibility. The ancient technological world may have been significantly more sophisticated than traditional history admits. Water should have been the greatest limitation for every settlement inside Batna province, yet ancient builders developed systems that appear specifically optimized for desert survival. Multiple aqueducts and underground channels were constructed below surface level to reduce evaporation from direct sunlight, while thick masonry insulated flowing water from extreme heat exposure. Certain hydraulic mortars used in the region show unusual resistance to cracking despite centuries of thermal cycling. Scientifically, this matters because desert environments destroy materials rapidly. Daily expansion and contraction place enormous stress on both stone and mortar, and modern concrete exposed to harsh climates often develops major degradation within decades if poorly engineered. Yet some Roman-era materials in Batna province survived nearly 20 centuries. Laboratory studies on Roman hydraulic concrete elsewhere in the Mediterranean revealed chemical reactions involving lime and volcanic ash capable of strengthening materials over time through mineral crystallization. Although North African mixtures differed from Italian marine concrete, some archaeologists believe regional formulas may have contained locally adapted mineral compositions. Modern science still struggles to reproduce completely. In practical terms, these systems functioned almost like passive climate control technology. Water remained cooler underground, thick masonry stabilized interior temperatures, and urban layouts improved airflow throughout the city. In some structures, the difference between exterior and interior temperatures may have significantly improved food preservation and human endurance during extreme heat. These were not simply architectural conveniences, they were environmental engineering systems designed to keep entire urban populations alive in one of the harshest climates connected to the Roman world. One of the greatest mysteries of Batna province is the extraordinary durability of its ancient structures. The region faces intense UV radiation, desert winds, thermal shock, earthquakes, and long-term desertification, yet many ruins have survived for nearly 2,000 years. Some walls still preserve extremely tight stone joints, despite having no steel reinforcement or modern cement. This becomes even more remarkable when many modern concrete structures can suffer major deterioration within only a few decades in harsh environments. Modern engineers believe some ancient construction systems may have been better optimized for weight distribution, flexibility, and thermal expansion resistance. The deeper researchers investigate these ruins, the harder the comparison becomes to explain. Using only hand tools and simple labor, ancient civilizations somehow built structures capable of surviving extreme environmental conditions for nearly 2,000 years. Do you think the ancient world once possessed engineering knowledge that modern civilization partially lost over time? Share your thoughts and theories in the comments below. El Sheikh Hamad hides the remains of the ancient city of Dur Katlimmu, a settlement that survived extreme heat, floods, earthquakes, and imperial collapse for centuries. Beneath layers of desert soil, archaeologists uncovered strange engineering systems, unusually durable mud brick structures, underground cooling chambers, and administrative records so advanced they resembled a proto-industrial logistics network. Some researchers now believe this forgotten Assyrian city possessed environmental engineering knowledge far beyond what historians once expected from the ancient Near East. The site began attracting major archaeological attention during German-led excavations in the 1970s and 1980s. Researchers identified the ruins as ancient Dur Katlimmu after discovering cuneiform tablets mentioning the city directly. What initially appeared to be another mud brick settlement soon revealed something much more complex. Excavations uncovered massive storage facilities, reinforced riverbank foundations, canal systems, and thousands of administrative tablets dating between the Late Bronze Age and Neo-Assyrian periods, roughly between 1500 BCE and 600 BCE. What shocked archaeologists most was the scale of organization. Dur Katlimmu was not a small provincial town. At its peak, the city controlled strategic trade moving along the Euphrates corridor connecting Mesopotamia, Anatolia, and the Levant. The number of tablets recovered suggested a bureaucratic system capable of tracking grain, labor, taxation, livestock, and military supplies with astonishing precision. Some scholars compared the complexity of the city's record-keeping to later Persian administrative systems that appeared centuries afterward. The greatest engineering mystery of El Sheikh Hamad lies in its mud brick architecture. Across the ancient Near East, mud brick was common because stone was scarce and expensive. The problem is that traditional mud brick deteriorates rapidly under environmental stress. Heat expansion, seasonal flooding, groundwater salts, and erosion usually destroy these structures within centuries unless they are constantly repaired. Yet parts of Dur Katlimmu remain standing after nearly 3,000 years. This becomes even more mysterious when considering the local climate. Summer temperatures in the region regularly exceed 40 degrees Celsius, while winter moisture and occasional Euphrates flooding create severe stress cycles in earthen materials. Under such conditions, ordinary adobe construction should fracture, soften, and collapse relatively quickly. Microscopic analysis of surviving bricks revealed unusual characteristics. Some bricks appeared denser than expected, with evidence of partial vitrification on outer layers, a phenomenon normally associated with low-temperature firing. Researchers found traces of clay mixed with fine gravel, organic fibers, ash particles, and mineral-rich sediments from the Euphrates floodplain. These mixtures may have functioned similarly to composite materials, distributing stress and reducing cracking. Some engineers believe the Assyrians may have unintentionally discovered a primitive stabilization process, similar to modern soil engineering. Organic fibers inside the bricks could have acted like micro-reinforcement, while ash additives may have altered moisture absorption rates. Experimental archaeology projects comparing reconstructed Assyrian bricks with standard adobe show that treated mixtures could survive significantly longer exposure to water and temperature fluctuation. The city's walls also reveal evidence of layered construction techniques. Instead of relying on single massive walls, builders often used multiple compacted layers with alternating material density. This resembles later seismic-resistant building principles used in parts of Persia and even Incan retaining systems thousands of kilometers away. The layered design may have reduced stress propagation during earthquakes or riverbank movement. Even more puzzling is the possibility that some exterior surfaces were intentionally heat-hardened after construction. Several wall fragments display mineral transformations suggesting exposure to controlled heating temperatures between approximately 400 and 700 degrees Celsius. If intentional, this would imply large-scale thermal treatment of architecture centuries before similar methods became common elsewhere in the region. No one fully understands how ancient builders developed these techniques without modern chemistry, structural engineering, or industrial kilns. Another major mystery involves the city's hydraulic engineering. Limu existed beside one of the most unpredictable rivers in the ancient world. The Euphrates could provide fertile agricultural land, but it also brought catastrophic flooding and riverbank erosion. Excavations revealed sophisticated canal networks, drainage pathways, reinforced embankments, and sediment control systems. Some riverbank foundations were constructed with alternating layers of compacted soil, gravel, and organic matter that appear specifically designed to absorb shifting pressure from floodwaters. This engineering approach resembles surprisingly modern geotechnical stabilization techniques. Similar principles are now used in flood control systems to prevent soil liquefaction and structural failure. Yet these ancient systems were built more than 2,500 years before modern hydrology emerged as a scientific discipline. Researchers also discovered evidence that water flow inside the city may have been partially regulated through elevation gradients rather than mechanical pumping. Slight changes in slope directed excess water away from residential districts while preserving underground moisture near storage areas and agricultural zones. Compared to many contemporary settlements that collapsed after repeated flooding, Limu demonstrated remarkable environmental resilience. Among the most intriguing discoveries were underground storage chambers maintaining temperatures significantly cooler than the surrounding environment. Even during intense summer heat, these subterranean facilities remained relatively stable. Archaeologists identified ventilation shafts and airflow channels positioned to maximize passive cooling through pressure differences and thermal circulation. Modern engineers comparing the structures to later Persian yakhchals and Middle Eastern wind towers found striking similarities in airflow logic. This suggests the inhabitants may have understood fundamental thermodynamic principles through empirical observation alone. Some grain storage rooms were built partially below ground with thick insulated walls and narrow openings minimizing heat transfer. Temperature simulations indicate that these chambers could preserve food supplies far longer than ordinary surface-level storage buildings in the same climate. If accurate, this would mean the people of Limu developed passive climate control architecture thousands of years before similar cooling concepts became widely documented elsewhere. The cuneiform tablets recovered from El-Sheikh Hamad reveal something equally astonishing. The city operated with extraordinary administrative complexity. Thousands of records documented food distribution, taxation, military movement, labor assignments, livestock inventories, and regional trade. The level of organization required for such management implies a highly efficient communication network connecting warehouses, officials, transport routes, and agricultural zones. Some historians estimate that maintaining this system would have required continuous coordination across hundreds of kilometers along the Euphrates trade corridor. This raises uncomfortable questions about how advanced Assyrian state infrastructure truly was. Traditional depictions often portray ancient empires as administratively primitive compared to later civilizations. But Durkat Limu suggests something closer to a centralized economic control system operating on near-industrial logistical principles. The city may not have possessed advanced machinery, but it clearly possessed advanced systems thinking. The region around the Euphrates has experienced geological activity for thousands of years, yet many parts of Durkat Limu survived for centuries. Excavations uncovered soft foundation layers made of compacted soil, gravel, and organic material beneath several major structures. Modern engineers believe these layers may have functioned like primitive shock absorbers, dispersing vibrations before they reach the upper walls. The principle is surprisingly similar to modern earthquake-resistant engineering. This suggests ancient builders may have developed construction knowledge over generations to help structures survive in an unstable geological environment. Do you think the engineers of Durkat Limu discovered construction techniques far ahead of their time? Or are we still underestimating how advanced ancient civilizations really were? Share your thoughts in the comments below. Northern Sudan, near the western bank of the Nile and roughly 100 kilometers north of the ancient Kushite capital of Napata, hides one of the strangest pyramid fields on Earth, Sedinga Pyramids. Unlike the gigantic monuments of Giza, these pyramids are small, crowded, and packed so tightly together that some are separated by less than 2 meters. More than 35 pyramids were discovered compressed into an area barely larger than a basketball court, creating one of the densest funerary landscapes ever identified by archaeologists. The site was first investigated systematically by French archaeological teams in the 20th century, but satellite surveys and later excavations revealed something unexpected. Beneath the shifting sands was not a single cemetery, but an evolving architectural system that had expanded for centuries with astonishing precision. What initially appeared to be ordinary Nubian tombs slowly became one of the most difficult engineering mysteries in ancient African archaeology. The civilization responsible was the Kingdom of Kush, one of the most powerful empires in northeastern Africa between roughly 800 BCE and 350 CE. For decades, historians underestimated Kushite engineering, often portraying it as a shadow of ancient Egypt. But Sedinga challenges that idea completely. The site demonstrates a level of spatial planning, material durability, and construction consistency that many researchers believe has not been fully explained even today. Unlike the pyramids at Giza, which relied on massive centralized labor forces and enormous limestone blocks, Sedinga operated under far harsher conditions. Temperatures in this region can exceed 45 degrees Celsius during the day before dropping dramatically at night. Wind erosion from the Sahara acts like continuous industrial sandblasting. Seasonal sand movement destabilizes foundations, and yet many of these pyramids survived for nearly 2,000 years. The first major mystery begins with the layout itself. Archaeologists discovered that the pyramid field expanded generation after generation without destroying earlier tomb systems below the surface. Ground-penetrating radar later revealed overlapping burial chambers extending beneath neighboring structures like an underground maze. In some cases, newer pyramids were built less than a meter away from older shafts descending several meters into unstable sediment. Modern engineers note that such construction would normally carry a serious risk of collapse. Digging too close to an older chamber could destabilize the surrounding soil and trigger chain failures across nearby structures. Yet catastrophic collapses appear surprisingly rare at Sedinga. This suggests the builders possessed an advanced practical understanding of subsurface load distribution and soil behavior, despite having no surviving mathematical manuals, no metal surveying instruments, and no architectural blueprints. The density of the site also creates another unresolved problem. Why build in such extreme compression at all? The surrounding desert offered enormous open space. Instead of spreading outward, the Kushites continued inserting new pyramids into already crowded zones with incredible geometric discipline. Researchers comparing the site to other ancient cemeteries noticed that the layout resembles efficient urban planning more than traditional funerary expansion. Some archaeologists even describe the arrangement as an ancient form of architectural compression, where sacred land was treated as a limited resource requiring precise optimization. The pyramid angles themselves remained remarkably consistent, despite centuries separating different construction phases. Many maintained slopes exceeding 40 degrees, requiring careful weight distribution to prevent structural failure in shifting sand environments. Maintaining such consistency over hundreds of years without modern measurement systems remains difficult to explain. But the greatest mystery at Sudeinga involves something far less glamorous than geometry or monuments. It involves mud brick. Most of the pyramids were constructed using combinations of mud brick and sandstone. On paper, this should have been a disastrous engineering choice. Mud brick is highly vulnerable to moisture fluctuations, thermal expansion, erosion, and structural fatigue. In desert climates, rapid temperature swings create repeated cycles of contraction and expansion that slowly fracture the material from within. Modern mud brick settlements in similarly harsh regions often deteriorate within decades, if not constantly maintained. Yet many pyramid cores at Sudeinga remained identifiable after nearly 2,000 years of exposure to extreme environmental stress. Researchers analysing surviving fragments found evidence that the Kushites may have engineered their bricks with unusually controlled clay compositions. Some samples contained exceptionally dense compaction layers, while others revealed traces of organic fibres that may have improved flexibility and crack resistance. The mystery is that no complete recipe survives. Scientists suspect plant materials, mineral additives, or even ash-based stabilizers could have been mixed into the mud. Certain plaster remnants also suggest the possibility of protective outer coatings resistant to abrasive sand erosion. The durability becomes even more shocking when compared with later civilizations. Some Roman mud brick structures in North Africa deteriorated faster, despite being built centuries afterward, using documented engineering techniques. At Sudeinga, however, sections of pyramid cores survived under conditions modern conservationists describe as extremely hostile. Wind moving across the Sahara can carry quartz-rich sand particles, capable of grinding exposed surfaces over time like mechanical polishing equipment. Yet traces of surface plaster survived on several structures. Researchers still debate whether the Kushites discovered a local mineral formula that improved resistance against erosion, or whether repeated maintenance cycles were organized through highly efficient labor systems now lost to history. There is also evidence that certain bricks were fired or partially heat-treated beyond ordinary sun-dried methods. Microscopic studies identified unusual hardness in specific fragments, raising questions about whether builders accidentally or intentionally created stronger ceramic-like layers. Experimental archaeology attempted to recreate similar compositions using Nile sediments and local clays, but matching the same durability has proven inconsistent. Even today, scientists cannot fully explain why some Sudeinga bricks resisted environmental destruction far better than expected. The deeper archaeologists excavated, the stranger the site became. Many pyramids belong not to kings, but to middle-ranking elites, priests, officials, and wealthy families. This suggests pyramid construction was not restricted to a tiny ruling class. Such widespread monument ownership implies a highly organized economic and labor network capable of producing standardized funerary architecture over generations. Quarrying stone, manufacturing bricks, Transporting materials, excavating burial shafts, and aligning structures all required coordinated specialists. Yet the surrounding region lacks evidence of gigantic imperial infrastructure on the scale seen in Egypt. Some experts now believe the Kushites developed an early modular construction system. Similar chamber layouts, repeated masonry styles, and consistent geometric proportions suggest builders followed standardized architectural templates that could be reproduced efficiently across different tombs. In effect, Sedenga may represent one of the earliest known examples of semi-standardized monument production in human history. Instead of constructing a few gigantic monuments, the Kushites created an expandable architectural network capable of functioning across centuries. Another mystery lies in the artistic remains scattered throughout the site. Nearby stood a temple dedicated to Queen Tai, wife of Pharaoh Amenhotep III of Egypt's 18th dynasty. Stone fragments discovered there reveal a fusion between Egyptian and Nubian artistic systems unlike almost anywhere else in ancient Africa. The carvings contain extremely fine incisions cut into fragile sandstone prone to cracking. Some lines remain visible despite centuries of erosion. Archaeologists still debate how artisans achieved such precision using bronze or early iron tools on inconsistent local stone. Even more unusual is the hybridization of styles. Egyptian symbolism was not merely copied, it was adapted. Structural elements appear modified for local environmental conditions, suggesting Kushite architects understood how to merge foreign architectural principles with regional engineering realities. Transporting the stone itself presents another unresolved problem. Large sandstone blocks had to be moved across unstable desert terrain in an environment with limited nearby timber resources. Traditional wooden roller systems would have been difficult to sustain at large scale. Some researchers suspect the Kushites relied on seasonal moisture, compacted sand pathways, sled systems, or coordinated human traction methods similar to those theorized for Egyptian construction. But no definitive evidence survives explaining how transport was managed so efficiently in one of the harshest landscapes in Africa. Perched on limestone cliffs nearly 70 meters above the Mediterranean coast of Cyprus, Kourian Archaeological site was destroyed in seconds by one of the most violent earthquakes of the ancient world. Yet beneath the collapsed columns and shattered villas, archaeologists discovered something unsettling, evidence that this city may have possessed engineering knowledge centuries ahead of its time. Modern excavations at Kourian accelerated during the 1930s under the direction of the University Museum of the University of Pennsylvania. What researchers uncovered was extraordinary. Entire districts frozen in the exact moment of destruction, caused by the massive earthquake of 365 AD, an event now estimated between magnitude 8.0 and 8.5. Bodies remained trapped beneath collapsed roofs. Stone columns had fallen in identical directions. Mosaics survived while surrounding walls disintegrated, and even today, Kourian remains one of the clearest archaeological earthquake snapshots ever discovered in the Roman world. The first mystery of Kourian begins with its location itself. The city was constructed directly above unstable coastal cliffs within one of the most seismically dangerous regions in the eastern Mediterranean. Cyprus lies near the boundary between the African and Eurasian tectonic plates, where stress accumulation has triggered destructive earthquakes for thousands of years. Modern geological surveys show the limestone beneath Kourian contains natural fractures capable of amplifying seismic waves. Under ordinary engineering logic, this should have made the site unsuitable for large stone architecture. Yet for nearly 700 years, Kourian supported massive Roman bath complexes, multi-story villas, aqueduct systems, granite columns weighing several tons, and a theatre capable of holding around 3,500 spectators. What confuses researchers is how the city remained structurally stable for centuries despite constant tectonic instability. Some engineers now believe the builders of Kourion understood practical earthquake behavior through long-term observation rather than mathematics. Similar patterns appear in ancient earthquake-resistant structures elsewhere in the Mediterranean, including Parthenon, Temple of Apollo at Delphi, and Pont du Gard. But Kourion may represent one of the most advanced examples because the entire city functioned on unstable coastal geology. One of the strangest discoveries at Kourion involves the way its buildings absorbed seismic force. Archaeologists found that many stone blocks were not rigidly cemented together. Instead, certain columns and foundation layers used flexible contact zones, allowing slight movement during tremors. In modern engineering, this resembles primitive seismic isolation systems. Some foundations contained alternating layers of crushed stone beneath heavier masonry, and these layers may have acted as shock absorbers, dispersing energy before it reached upper structures. The same principle appears in modern anti-earthquake architecture used in Japan and California. The theatre of Kourion is especially puzzling because despite repeated earthquakes over nearly 2 millennia, much of its curved seating structure survived remarkably well compared to nearby rectangular buildings. Researchers studying ancient structural mechanics noticed several unusual features. Curved geometry distributed stress more evenly, stone seating rows acted as interlocking stabilizers, and open-air construction reduced roof collapse pressure. Even more mysterious is the precision of the load distribution. Modern simulations suggest some sections of Kourion's architecture approach stability ratios comparable to later Byzantine seismic designs developed centuries afterward. No surviving Roman texts fully explain how such engineering knowledge was standardized. Kourion ancient theatre is not only structurally strange, it also possesses unusually advanced acoustic behavior. Today, visitors standing at the center of the stage can still be heard clearly from the upper seating rows, despite intense sea winds from the Mediterranean coast. Acoustic tests conducted at similar Greco-Roman theatres show speech intelligibility often remains above 90% across large seating areas without amplification. At Kourion, the geometry appears almost mathematically optimized. The semicircular arrangement minimizes echo distortion. Limestone surfaces reflect mid-frequency human speech efficiently, and the slope angle enhances sound projection naturally. What makes this mysterious is that the theatre predates formal acoustic science by more than 1,000 years. Ancient architects seemingly achieved sophisticated sound engineering entirely through empirical experimentation. Comparable acoustic anomalies exist at Epidaurus Ancient Theatre and Aspendos Theatre, yet Kourion's exposure to ocean winds should theoretically reduce clarity significantly. Instead, the site still produces highly intelligible sound conditions even today. The greatest mystery of Kourion lies inside the house of Eustolios. More than 1,500 years after the earthquake, many mosaics still preserve astonishing color intensity despite exposure to moisture, salt air, temperature fluctuations, and structural collapse. For conservators, this should not happen. Scientific analysis of the mosaics revealed several extraordinary characteristics. Mineral pigments contained unusually stable iron oxides and copper-based compounds. Lime mortar layers displayed extremely low salt penetration, and tesserae placement reduced internal cracking during seismic vibration. Some sections maintain visible detail after surviving conditions that normally destroy Roman floor art within centuries. Researchers comparing Kourion's mosaics to those at Pompeii Archaeological Park, Villa Romana del Casale and Antioch Mosaic Museum notice something unusual. The mortar beneath Curion's mosaics appears exceptionally resistant to both humidity and microfracturing. Modern laboratory studies suggest the lime mixture may have undergone prolonged chemical curing, similar to advanced Roman marine concrete. Some samples contain microscopic crystalline bonding structures that strengthen over time when exposed to moisture. This has led to speculation that builders in Curion possessed localized material formulas now completely lost. Even more mysterious is how certain mosaic panels survived intact while surrounding stone walls collapsed entirely during the 365 AD earthquake. Some researchers suspect the flooring system itself distributed seismic stress differently from vertical masonry. In other words, the mosaics may not only have been decorative, they may also have been engineered for structural resilience. The destruction layer of 365 AD remains one of the most important earthquake records in archaeology. The earthquake likely originated near Crete and generated a massive tsunami across the eastern Mediterranean. Ancient historian Ammianus Marcellinus described entire coastlines being devastated. At Curion, evidence suggests the shaking intensity reached catastrophic levels. Columns snapped at their weakest stress points. Roof beams collapsed almost simultaneously. Human remains indicate many inhabitants died instantly, and entire residential sectors were abandoned afterward. Yet the destruction pattern remains inconsistent. Some areas were pulverized, while others survived surprisingly well only meters away. Modern geophysicists believe this may involve seismic wave amplification caused by cliff edge resonance, a phenomenon where certain geological formations magnify earthquake energy unpredictably. This effect has also been documented during modern earthquakes in Mexico City and parts of Turkey. But Curion presents one of the oldest known examples preserved archaeologically. Supplying water to a city built on unstable cliffs should have been nearly impossible, yet excavations uncovered a remarkably advanced hydraulic system, including ceramic pressure pipes, gravity-fed reservoirs, sediment control basins, and water distribution channels maintaining steady flow across uneven terrain. The precision of pipe alignment is especially impressive. Some ceramic sections fit together with millimeter-level accuracy despite being produced nearly 2,000 years ago. Even modern engineers acknowledge that maintaining hydraulic stability in seismic coastal terrain remains extremely difficult. What is astonishing is that parts of Curion's water infrastructure survived multiple earthquakes before the final destruction. Do you think Curion was abandoned because of fear, religion, or because its ancient engineering knowledge was permanently lost? Share your thoughts in the comments below. Beneath the jungles of western Belize, near the modern village of San Ignacio, Barton Creek Cave cuts through limestone mountains like a flooded artery from another world. For more than 7 kilometers, a dark underground river disappears into total blackness. No sunlight reaches most of the system. Oxygen levels fluctuate. Sharp limestone hangs from the ceiling like teeth. Yet over 1,000 years ago, the ancient Maya repeatedly entered this cave carrying ceramic vessels, incense burners, human remains, fire, and ritual offerings deep into the darkness. Some artifacts were found nearly 2 kilometers from the entrance. Even today, trained explorers using electric lights and modern boats struggle to navigate sections of the cave safely. The terrifying question is simple. How did an ancient civilization without modern mapping technology master an underground labyrinth so dangerous that much of it remains unexplored even now? The cave first drew archaeological attention during the 20th century, but systematic investigation accelerated in the 1970s and 1980s when researchers began discovering dense concentrations of Maya ceremonial material inside the flooded chambers. Excavations later revealed pottery fragments, calcite-covered skulls, sacrificial remains, and ceremonial platforms dating primarily between 200 and 900 CE during the Maya Classic period. What shocked archaeologists was not merely the quantity of objects, but their location. Many had been deliberately placed in areas requiring long canoe journeys through absolute darkness. Some artifacts rested on elevated ledges accessible only through narrow passages above deep water. This was not accidental wandering. It was organized movement through an environment most humans instinctively avoid. For the Maya, caves were believed to be entrances to Xibalba, the underworld described in the Popol Vuh. But Barton Creek appears to have been more than a symbolic religious site. Evidence suggests the cave functioned as a highly controlled ceremonial complex requiring advanced environmental knowledge, spatial memory, and logistical coordination. In some ways, the engineering mystery of Barton Creek resembles the underground precision seen in places like Derinkuyu Underground City or the hidden hydraulic systems beneath Teotihuacan. Yet Barton Creek differs because the Maya were not constructing a tunnel network from scratch. They were adapting a naturally hostile geological system into a functioning ceremonial route deep underground. One of the greatest unresolved mysteries is navigation. Inside Barton Creek Cave, visibility beyond torchlight would have been nearly zero. The underground river bends repeatedly, and sound echoes violently against the limestone walls. Modern cave divers often describe similar flooded systems as psychologically disorienting environments where humans rapidly lose directional awareness. Yet the Maya repeatedly transported fragile ceramic vessels through these passages without destroying them. Researchers estimate that some ritual journeys may have lasted several hours. This implies a remarkably accurate internal understanding of the cave's structure. Archaeologists have proposed several theories explaining how the Maya navigated the darkness. Some believe generations memorized the cave through oral transmission, effectively creating a living mental map. Others suspect that airflow patterns, water acoustics, and rock formations served as natural orientation markers. Studies in human spatial cognition show that experienced navigators can develop acoustic mapping abilities in dark environments, using echoes to estimate chamber size and passage direction. Blind individuals using echolocation demonstrate similar neurological adaptation today. If the Maya intentionally trained ritual specialists inside Barton Creek over generations, they may have developed environmental navigation skills far beyond what modern people expect from ancient societies. The problem of light creates another major technical mystery. Most ceremonial areas inside Barton Creek would have required sustained illumination, yet fire inside confined caves presents serious dangers. Torches rapidly consume oxygen while producing carbon dioxide and smoke. In poorly ventilated chambers, this can become fatal. However, soot accumulation inside Barton Creek appears lower than expected considering the amount of ritual activity that occurred there. Some archaeologists believe the Maya deliberately selected chambers with natural air circulation created by pressure differences within the cave system. Temperature studies in similar limestone caves show that narrow vertical shafts can produce stable convection currents, naturally pulling smoke away from occupied areas. In other words, the Maya may have understood underground airflow well enough to operate within the cave without suffocating themselves. Even more fascinating is the role of water transportation. Unlike many Maya caves accessed primarily on foot, Barton Creek contains long, navigable river passages. Modern exploration often requires canoes because portions of the cave remain permanently flooded. Maneuvering wooden boats through tight limestone corridors in darkness would have demanded extraordinary coordination. A single collision could shatter ceramic offerings or overturn passengers into deep cold water. Yet hundreds of delicate artifacts survived intact. This strongly suggests repeated controlled travel through predetermined ceremonial routes. Some researchers compare Barton Creek's underground canoe navigation to Polynesian open ocean navigation techniques. Polynesian sailors crossed thousands of kilometers of Pacific Ocean without compasses by memorizing wave behavior, wind direction, and star movement. The Maya inside Barton Creek may have relied on an underground equivalent. Subtle water flow patterns, echoes, rock textures, or even airflow changes guiding movement through darkness. Such knowledge would not appear in written records because it was likely transmitted through ritual training and direct experience. Human remains discovered inside the cave deepen the mystery further. Archaeologists found skeletons of both adults and children placed in remote chambers far from the entrance. Some bones show evidence consistent with sacrificial practices, though interpretations remain debated. Transporting bodies through flooded passages into difficult-to-access chambers would have required significant physical effort and planning. This suggests ritual meaning outweighed practical difficulty. Certain skeletal deposits were positioned near water pools or acoustically resonant chambers, leading some researchers to suspect that sound itself played an important role in Maya ceremonies. Acoustic studies inside ancient ritual structures around the world have revealed surprising intentionality. At sites like Chavinda Huantar, underground passages were engineered to distort sound and create psychological effects during ceremonies. Barton Creek was not artificially carved to the same degree, yet natural chambers inside the cave produce unusual resonance patterns. Dripping water, echoing voices, and amplified footsteps could have transformed rituals into overwhelming sensory experiences. In complete darkness, sound becomes spatial architecture. The Maya may have intentionally chosen ceremonial chambers based on these acoustic properties. But perhaps the most astonishing mystery involves preservation. Barton Creek Cave exists in an environment that should destroy artifacts rapidly. Humidity inside the cave remains extremely high year-round. Water constantly moves through the system. Organic materials exposed to moisture usually decompose quickly due to bacterial and fungal activity. In tropical surface environments, many materials deteriorate within decades. Yet inside Barton Creek, archaeologists recovered ceramics, bone fragments, and even delicate surface details preserved for over 1,000 years. This preservation paradox has become one of the most scientifically intriguing aspects of the cave. Researchers discovered that Barton Creek maintains a remarkably stable microclimate. Temperatures remain close to 24 to 25 degrees Celsius throughout most of the year, with minimal fluctuation. In addition, the cave's airflow and mineral-rich water chemistry may actively inhibit certain forms of biological decay. Calcite deposition slowly coats objects with a protective mineral layer, almost sealing them in stone over time. Some pottery fragments appear partially fossilized beneath thin, crystalline coatings. The preservation conditions have been compared to other extraordinary archaeological environments such as the dry tombs of Valley of the Kings or the frozen burials of the Pazyryk culture in Siberia. But Barton Creek is different because it achieves preservation inside a wet tropical environment where decay should dominate. Scientists still do not fully understand how humidity, mineral saturation, oxygen variation, and microbial ecosystems interact within the cave to slow deterioration so effectively. Studies of cave microbiology suggest another possibility. Certain mineral-rich cave systems contain microbial communities that suppress destructive bacteria and fungi. Similar phenomena have been observed in European caves preserving prehistoric paintings for tens of thousands of years. If Barton Creek possesses a unique subterranean microbial balance, it may partially explain why fragile materials survive for centuries despite constant moisture exposure. What do you think the Maya were truly doing deep inside Barton Creek Cave? Simple rituals, or something far more advanced than we understand today? Share your thoughts in the comments below. Dry highlands in central Turkey, nearly 1,500 meters above sea level, conceal enormous stone walls stretching across the Anatolian Plateau, like the remains of a forgotten fortress city. For centuries, these ruins were believed to belong to a relatively minor settlement. That changed in the late 20th century when archaeologists began systematic surveys using aerial photography, satellite imaging, and large-scale geomagnetic scanning. What emerged beneath the soil shocked researchers. Hidden under the landscape was an enormous planned city covering nearly 2.5 square kilometers, surrounded by more than 7 kilometers of defensive walls, reinforced by hundreds of towers and gates. The city appeared to have been built rapidly during the 6th century BCE and then destroyed by fire only a short time later. Unlike most ancient cities that evolved gradually over centuries, Kirkenes seemed to appear almost fully formed from the beginning. That single detail transformed the site into one of the strangest archaeological mysteries in Anatolia. The first mystery surrounding Kirkenes is the sheer speed and scale of its construction. Archaeologists estimate that the outer fortification walls alone required millions of stones. Some wall sections were more than 4 meters thick, extending across rugged hills and steep terrain with remarkable consistency. For comparison, many fortified Iron Age cities in Anatolia are far smaller and developed incrementally over generations. Kirkenes, however, resembles a sudden state engineering project more comparable to imperial capitals of Assyria or later Persian administrative centers. The logistical problem becomes almost difficult to comprehend. Without cranes, industrial metal tools, or wheeled transport systems capable of handling heavy stone efficiently across mountainous terrain, ancient builders somehow organized labor, quarrying, transport, and construction on a gigantic scale. Researchers studying labor estimates suggest that even with thousands of workers operating simultaneously, construction may have required an extremely centralized authority with advanced planning systems. The city's uniformity strongly implies pre-designed urban engineering rather than organic growth. That level of coordination in Iron Age Anatolia remains deeply unusual. Kirkenes does not merely look defensive, it appears engineered entirely around military logic. The walls zigzag across the plateau instead of following simple straight lines, creating overlapping defensive angles that allowed defenders to attack invaders from multiple directions simultaneously. Many medieval fortresses later adopted similar principles, yet Kirkenes demonstrates them centuries earlier. The gates are equally mysterious. Instead of wide, direct entrances, several access points force movement through narrow turning passages where invading forces would become trapped and exposed. Archaeologists believe these choke point systems were intentionally designed to maximize defensive advantage. What makes this strange is that neighboring cultures of the same era often relied on much simpler defensive architecture. Kirkenes suggests a society with unusually advanced understanding of battlefield geometry and controlled urban defense. Some researchers even compare the city's layout to a giant engineered security system rather than a conventional settlement. One of the most revolutionary aspects of Kirkenes is how modern technology revealed the city without excavation. Archaeologists used magnetometry surveys capable of detecting buried stone structures and burnt materials beneath the ground. The results exposed an entire hidden urban grid. Streets, districts, compounds, workshops, and ceremonial areas appeared with astonishing clarity. The scans revealed something even more puzzling. The city followed a highly organized plan. Roads intersected in controlled patterns, major structures occupied strategic positions, and the urban design appeared coordinated across the entire settlement. Ancient cities usually evolve unevenly over centuries, producing chaotic layouts. Kirkenes instead resembled a modern planned capital, designed from the beginning according to a master blueprint. This raises a disturbing historical question. If Iron Age builders in Anatolia could organize urban planning at this level, how many other primitive civilizations may have possessed forms of engineering sophistication that archaeology still underestimates? At some point in the 6th century BCE, Kirkenes was consumed by a massive fire. Thick destruction layers and burned debris appear across large sections of the city. Yet the most mysterious detail is what happened afterward. Almost nothing. Most strategically located ancient cities were rebuilt repeatedly after destruction. Troy was reconstructed multiple times. Babylon survived successive invasions. Hattusa rose and fell across different eras. Kirkenes, however, was largely abandoned forever. This is extremely unusual considering its enormous walls and dominant position overlooking the Anatolian plateau. Archaeologists still debate whether the city was destroyed during warfare, internal collapse, or deliberate evacuation followed by systematic burning. Some theories connect the destruction to the expansion of the Persian Empire under Cyrus the Great, while others associate it with regional political collapse. But no explanation fully clarifies why such an enormous and expensive city vanished almost instantly from history. Another unresolved mystery is sustainability. Kirkenes stood in a relatively harsh environment where maintaining a large urban population would have been difficult. Ancient cities depended entirely on reliable supplies of water, timber, grain, livestock and fuel. Yet evidence suggests Kirkenes may have supported thousands of inhabitants within fortified walls. The engineering challenge becomes enormous when compared to similar settlements. Researchers estimate that ancient urban populations required vast quantities of food transported constantly from surrounding agricultural zones. Water management alone would have been critical. However, archaeologists have not fully explained how Kirkenes sustained itself logistically during its short existence. This has led some historians to propose that Kirkenes may not have functioned as a traditional permanent city at all. Instead, it may have operated as a massive military administrative centre or emergency royal capital designed for strategic control during periods of regional instability. If true, the city may represent one of the earliest examples of large-scale temporary geopolitical engineering in ancient Anatolia. Several parts of Kirkenes appear aligned carefully with the surrounding terrain and defensive sightlines. Elevated structures command wide views over the plateau, while road systems seem optimized for controlled movement across the city. This level of urban precision is particularly strange because it emerged in an era supposedly limited by relatively primitive surveying methods. Ancient engineers likely relied on ropes, wooden measuring rods, solar observations, and manual geometry. Yet the resulting city demonstrates remarkable consistency across enormous distances. Comparisons are often made with other ancient planned cities such as Mohenjo-Daro in the Indus Valley or the orthogonal street systems later perfected by the Romans. However, Kirkenes differs because it combines planned urbanism with extreme militarization. The city feels less like a civilian settlement and more like a giant strategic instrument embedded directly into the landscape. Perhaps the greatest mystery is the identity of the people who built it. Some archaeologists associate Kirkenes with the Medes, an Iranian people who briefly dominated parts of Anatolia before the Persian Empire emerged. Others argue the city may represent a local Anatolian power attempting to imitate imperial models from Assyria and Mesopotamia. The uncertainty matters because Kirkenes seems too ambitious for an ordinary regional kingdom. Building a city of this scale required immense labour organisation, political authority, engineering knowledge, and economic resources. Whoever constructed Kirkenes possessed capabilities far beyond what historians once assumed for Iron Age Anatolia, and yet the civilization behind the city left surprisingly little written evidence. No surviving inscriptions fully explain its purpose, rulers, or sudden destruction. The city remains largely silent. What do you think Kirkenes really was? A forgotten imperial capital, a giant military experiment, or evidence that ancient engineering was far more advanced than we realize? Share your thoughts in the comments below. About 160 kilometers north of Luxor, near the edge of the Nile Valley Desert, lies Abydos Temple Complex, one of the oldest sacred cities in Egyptian history. Archaeologists began major excavations here during the 19th century, but the site became globally controversial after researchers uncovered the massive subterranean Osiraion structure behind the Temple of Seti first. Unlike the decorated limestone temple above it, the Osiraion was built from enormous granite blocks weighing up to 70 tons each. Its engineering appeared older, heavier, and strangely disconnected from the architectural style of New Kingdom Egypt. The deeper excavations went, the stranger Abydos became. Hidden chambers, precision-cut stone surfaces, unexplained water erosion, astronomical alignments, and controversial carvings transform the site from a religious monument into one of the greatest ancient technological mysteries ever discovered. The Osiraion is the single most mysterious structure in Abydos. Buried below ground level and surrounded by water channels, it looks dramatically different from the refined decorative temples of dynastic Egypt. Instead, it resembles the megalithic style seen at sites like Puma Punku in Bolivia or the platform stones of Baalbek in Lebanon. Its granite blocks are enormous, some weigh between 50 and 70 tons, and were transported from Aswan, over 150 kilometers away. Even today, moving stones of that size requires cranes, hydraulic systems, and carefully engineered transport platforms. Yet the Egyptians somehow moved, aligned, and fitted these blocks with astonishing precision over 3,000 years ago. What confuses researchers most is the construction quality. Many joints between stones are so tight that a modern razor blade cannot fit between them. Some surfaces appear machine polished. Others contain unusually straight internal angles rarely achieved with simple copper tools. Experimental archaeology has shown that cutting granite with copper saws and quartz sand is technically possible, but reproducing Abydos-level precision requires extraordinary labor and time. Some engineers argue the efficiency implied by the Osiraion simply does not match the accepted technology of the Bronze Age. Even stranger is the erosion. Several lower granite surfaces show patterns resembling prolonged water exposure. Geological comparisons have led some alternative researchers to suggest the Osiraion may predate dynastic Egypt entirely, possibly originating during a wetter climatic period thousands of years earlier. Mainstream Egyptology disputes this theory, yet the erosion patterns continue fueling debate. Inside the Temple of Seti First, the stonework reaches a level of refinement difficult to explain using primitive tools alone. The temple walls contain thousands of deeply engraved hieroglyphs with nearly identical depth and spacing. Columns stand with near-perfect symmetry. Flat granite surfaces show deviations of only millimeters across several meters. Granite is one of the hardest stones commonly used in ancient construction. Its quartz crystals rate around 7 on the Mohs hardness scale, while copper tools rank around 3. This means the Egyptians were technically working with tools softer than the stone itself. Modern reconstructions suggest workers may have used quartz sand as an abrasive, essentially grinding the granite rather than cutting it directly. However, the precision seen at Abydos rivals certain machine-assisted masonry techniques. Circular drilling marks discovered on some Egyptian granite artifacts elsewhere in Egypt indicate penetration rates that some engineers consider unusually high for manual drilling systems. Comparisons are often made with the Inca stonework at Sacsayhuaman or the polygonal walls of Ollantaytambo. Yet Abydos differs because many surfaces here are not only tightly fitted but geometrically uniform. Some researchers speculate the Egyptians may have possessed advanced lost techniques involving vibration-assisted cutting, chemical softening of stone, or highly specialized abrasive systems never fully documented in surviving records. Among the most famous mysteries at Abydos are the so-called helicopter hieroglyphs. Located high on a temple beam, several overlapping carvings appear to resemble a helicopter, submarine, jet aircraft, and even a tank. Mainstream Egyptologists explain the phenomenon as a palimpsest, an effect created when older hieroglyphs were plastered over and later recarved by another pharaoh. Over centuries, erosion exposed both layers simultaneously, accidentally creating modern-looking shapes. Scientifically, this explanation is reasonable. Yet the controversy persists because the resemblance is remarkably specific. Millions of visitors have seen the carvings, and the images spread globally as supposed evidence of lost technology or ancient knowledge. What makes the debate more interesting is not necessarily the carvings themselves, but what they represent psychologically. Abydos repeatedly confronts researchers with structures and engineering choices that already feel technologically advanced. The helicopter hieroglyphs became symbolic of a larger question: how much ancient knowledge has truly been lost? The layout of Abydos appears deeply connected to astronomy. The temple axis aligns with celestial patterns associated with Osiris, often linked symbolically to the Orion constellation. Ancient Egyptian texts repeatedly connect the soul of the pharaoh with stars in Orion's belt. During specific times of the year, sunlight travels through dark corridors and illuminates interior chambers with striking accuracy. Achieving this effect required careful calculations involving solar angles, seasonal movement, and architectural orientation. This phenomenon can also be seen at Abu Simbel, where sunlight reaches the inner sanctuary only twice per year, and at Newgrange in Ireland, where the winter solstice sun penetrates a narrow stone passage precisely at dawn. Yet Abydos contains a more labyrinth-like internal design, making its alignments especially difficult to engineer. Some archaeoastronomers argue that ancient builders possessed observational astronomical knowledge far beyond what is commonly assumed. Without telescopes or modern instruments, they tracked celestial movement accurately enough to orient massive stone complexes over long distances with minimal error. Several chambers inside Abydos produce unusual acoustic effects. Deep sounds resonate for extended periods, and low frequencies appear amplified within enclosed stone rooms. Visitors often describe a heavy vibrating sensation when speaking inside certain sections of the Osirion. Acoustic specialists studying ancient monuments have noted similar effects in Malta's Hippogeum, the Mayan pyramid at Chichen Itza, and Neolithic passage tombs across Europe. In some structures, specific frequencies can alter human perception, concentration, and emotional response. The granite used in the Osirion may also contribute to resonance behavior. Granite contains quartz crystals capable of piezoelectric effects under pressure, although no evidence proves the Egyptians intentionally used this property technologically. Still, the repeated appearance of resonance chambers in sacred ancient sites has led some researchers to question whether sound played a larger ritual or psychological role in ancient civilizations than previously believed. Modern ground-penetrating radar surveys around Abydos have revealed buried anomalies beneath the surface, including linear formations and possible voids near the Osirion. Some archaeologists believe entire sections of the ancient sacred city remain hidden beneath layers of Nile sediment. This possibility is significant because Abydos was continuously occupied and rebuilt over thousands of years. Like Troy or Jerusalem, newer civilizations repeatedly constructed temples atop older foundations. If deeper layers exist, they could potentially preserve structures from Egypt's earliest dynastic periods, or perhaps even older unknown phases of occupation. Satellite archaeology has already transformed Egyptian exploration in recent decades. Infrared imaging has revealed buried settlements, lost pyramids, and hidden road systems elsewhere across Egypt. Abydos may still conceal major discoveries waiting beneath the desert floor. One of Abydos' most historically important discoveries is the Abydos King List, a chronological sequence of pharaohs carved into the temple walls. Yet several rulers are deliberately missing, including Akhenaten, Tutankhamun, and other controversial figures connected to religious upheaval. This was not an accident. Ancient Egyptian rulers intentionally edited history. Pharaohs considered illegitimate or dangerous were removed from official records in an attempt to erase their memory entirely. The practice reveals something unsettling about ancient civilizations. Historical records were controlled narratives, not objective archives. If entire rulers could disappear from official inscriptions, researchers must ask how much additional knowledge vanished over the centuries. Do you think the mysteries of Abydos temple complex prove that ancient civilizations possessed lost knowledge far beyond what modern history accepts? Share your thoughts in the comments below. The ruins of Cherven Fortress rise above the limestone cliffs of northeastern Bulgaria like the remains of a vanished military machine. Archaeologists believe the fortress reached its peak during the Second Bulgarian Empire in the 13th and 14th centuries, controlling major trade and military routes across the Balkans. But what transformed Cherven from a forgotten medieval ruin into one of the region's greatest engineering mysteries was not simply its age or destruction. It was the discovery that nearly every part of the fortress appears to solve technical problems that should have been almost impossible for its era. Massive defensive walls were anchored directly into unstable cliff rock. Sophisticated water systems operated hundreds of feet above the river below. Multi-layered fortifications showed structural logic similar to far later military architecture, and some construction materials have survived for more than 7 centuries with a durability researchers still struggle to fully explain. The site was first systematically investigated during the late 19th century after local scholars reported unusual stone ruins spread across the plateau. Early excavations revealed towers, churches, underground passages, workshops, streets, and enormous defensive walls extending across the cliff edges. Archaeologists eventually discovered that Cherven once covered more than 1 square kilometre and may have housed several thousand inhabitants during its peak. What shocked researchers most was the complexity hidden beneath what initially appeared to be a simple medieval fortress. The deeper they excavated, the more the site resembled a highly engineered defensive city, carefully adapted to an impossible landscape. The first major mystery involves the terrain itself. Cherven was built on fractured limestone plateaus overlooking deep valleys nearly vertically cut into the landscape. Even with modern machinery, constructing a stable fortified city on such terrain would be extremely difficult. Yet medieval builders somehow created flat structural platforms, aligned walls with remarkable precision, and distributed enormous weight across unstable rock formations. Some surviving walls remain surprisingly straight despite centuries of earthquakes, erosion, freezing winters, and temperature expansion. Archaeological surveys show that many foundations were not simply placed on rock, but actually interlocked into carved bedrock channels. This technique dramatically increased stability and prevented lateral collapse. Engineers comparing Cherven to other mountain fortresses estimate that thousands of tons of stone had to be transported uphill without modern lifting systems. Some individual blocks weigh several hundred kilograms. The precision of these constructions becomes even more puzzling when compared to the technology available during the 13th century. Medieval Balkan builders primarily relied on iron chisels, wooden cranes, ropes, sledges, and animal labor. Yet several wall sections display alignment errors of only a few centimeters over long distances. Similar precision is often associated with much later military engineering traditions. Researchers have compared the logistical difficulty of Cherven's construction to sites like Machu Picchu and Masada, both famous for solving impossible architectural challenges in extreme terrain. But the greatest mystery of Cherven may be water. The fortress sits approximately 200 meters above the river below, yet historical evidence suggests the city could survive prolonged sieges involving thousands of people. Medieval armies often relied on cutting water access to destroy elevated fortresses, but Cherven appears to have developed unusually advanced solutions to this problem. Excavations uncovered reservoirs carved directly into bedrock, underground cisterns, ceramic pipe fragments, drainage systems, and channels designed to collect and store rainwater. Some cisterns remain partially waterproof even today. Researchers attempting to calculate the fortress's water supply encountered a serious problem. Average rainfall in the region appears insufficient to sustain the estimated population during long military blockades. This has led to theories that additional underground water systems remain undiscovered beneath the fortress. Ground-penetrating radar surveys have identified several buried anomalies that may represent tunnels or concealed chambers connected to hidden reservoirs. Some archaeologists believe Cherven may have employed gravity-fed hydraulic systems similar to those seen in Byzantine engineering centers. Others suggest deep vertical wells could still exist beneath collapsed structures. The waterproofing material inside certain reservoirs presents another unexplained puzzle. Chemical analysis suggests mixtures of lime mortar combined with crushed ceramics and mineral additives. This resembles ancient hydraulic concretes used by the Romans and Byzantines, materials specifically engineered to resist moisture penetration. Some samples display crystalline bonding patterns that continue strengthening over time, similar to self-healing reactions identified in Roman marine concrete. If confirmed, this would suggest that builders in medieval Bulgaria possessed advanced empirical knowledge of long-term material durability that was never formally documented. The fortress towers themselves reveal another astonishing level of engineering sophistication. The central defensive tower, one of Cherven's most recognizable structures, contains unusually strategic wall reinforcement patterns. Rather than maintaining uniform wall thickness, builders concentrated heavier masonry in zones most vulnerable to attack or structural stress. Modern structural engineers note that this resembles load distribution principles used in far later military fortifications. Some internal layers alternate between brick and stone, possibly helping absorb impact energy from siege weapons. During the 13th and 14th centuries, trebuchets capable of launching projectiles weighing over 100 kilograms were becoming increasingly common across Europe and the Middle East. Cherven's architecture appears specifically optimized to resist these forces. This raises a difficult historical question. How did local builders acquire such sophisticated engineering knowledge? Very few surviving texts describe the technical construction methods used at Cherven. Some historians believe Byzantine military engineers may have transferred advanced architectural concepts into Bulgaria during periods of political alliance and warfare. Others argue the fortress represents centuries of accumulated regional experimentation, gradually refined through conflict. Yet much of this knowledge vanished after the Ottoman expansion into the Balkans during the late 14th century. Another major mystery surrounds the durability of the masonry itself. Many surviving structures have endured over 700 years of rain, frost cycles, earthquakes, biological growth, and thermal stress. Some mortar joints remain surprisingly intact despite complete exposure to the environment. Laboratory analysis indicates unusually fine particle distribution within the mortar mixtures, allowing tighter bonding between stone layers. Certain walls also contain hidden brick inclusions, acting almost like internal shock absorbers. Comparisons with other medieval European fortresses reveal that Cherven's preservation is unusually strong considering the harsh climate conditions of northeastern Bulgaria. Winter temperatures in the region frequently fall below freezing, causing repeated expansion and contraction inside stone cracks. Over centuries, this process destroys most exposed masonry. Yet parts of Cherven continue standing at heights exceeding 10 meters. Researchers suspect builders intentionally designed drainage systems inside the walls themselves, preventing trapped moisture from accumulating and freezing internally. Similar anti-moisture engineering techniques appear in some late Byzantine fortifications, but remain poorly understood. Archaeologists discovered that Cherven was far more than a military fortress. Excavations revealed churches with frescoes, workshops, metal production areas, storage facilities, homes and paved roads. The city was organized into layered defensive zones, allowing defenders to retreat upward into safer sectors during attacks without losing the entire fortress. This resembles early forms of defense in depth, long before such military strategies became common. Even more mysterious are the underground spaces that remain largely unexplored. Surveys detected hidden voids beneath collapsed structures, possibly leading to escape tunnels, storage chambers, or additional water systems. Because much of Cherven still has not been excavated, the fortress continues revealing new mysteries even today. Do you think the builders of Cherven possessed engineering knowledge far beyond what historians believe medieval societies were capable of? Share your thoughts in the comments below. Chambers Pillar rises alone in the Red Desert of Central Australia, nearly 160 kilometres south of Alice Springs. Standing roughly 50 metres tall, this isolated sandstone column has survived in one of the harshest environments on Earth for tens of millions of years. But the deeper researchers studied the pillar and the ancient Aboriginal pathway surrounding it, the stranger the site became. Long before maps, roads or compasses existed in Australia's interior, people were already navigating enormous desert distances with astonishing precision, using stars, songs, geological landmarks, and environmental memory systems that modern science still struggles to fully understand. The site entered Western records in 1860 when explorer John McDowell Stewart passed through the region during his attempt to cross Australia from south to north. Stewart named the formation after James Chambers, one of his financial supporters. Yet Aboriginal communities had known the pillar for thousands of years as part of a much older network of ceremonial and navigational routes embedded into the landscape itself. What makes Chambers Pillar unusual is that the mystery is not hidden underground. The mystery is the landscape itself. Unlike Stonehenge or the pyramids, Chambers Pillar contains no giant architecture, no carved temple complex, and no massive engineered walls. Instead, the anomaly lies in how ancient humans transformed an empty desert into a functioning information system without writing, machines, or visible infrastructure. One of the greatest mysteries surrounding Chambers Pillar is the ancient navigation network connected to it. The Australian interior is brutally hostile. Summer ground temperatures can exceed 60 degrees Celsius, annual rainfall is extremely low, and many regions contain almost no permanent water sources. Modern travellers crossing these environments require GPS systems, satellite communication, and carefully calculated fuel supplies. Yet, Aboriginal groups crossed these deserts repeatedly for trade, ceremonies, and migration long before modern technology existed. Researchers studying Aboriginal songlines discovered that many routes were encoded into oral traditions that functioned almost like living maps. Specific verses corresponded to hills, waterholes, rock formations, and travel directions. In some cases, the rhythm and sequence of songs mirrored the physical geography of the route itself. A traveller who memorised the song could theoretically navigate hundreds of kilometres across featureless terrain. What makes this system extraordinary is its accuracy. Anthropologists have documented songline routes extending across massive sections of Australia, some connecting regions separated by more than 3,000 kilometres. In practical terms, this meant ancient travellers could maintain continent-scale navigation without written maps. Chambers Pillar appears to have functioned as one of these major desert markers. Rising dramatically above the surrounding plains, the formation is visible from great distances and would have acted like a natural beacon in an environment where even slight navigational errors could become fatal. Some researchers compare the system to a biological GPS network. Instead of satellites and digital coordinates, the system integrated astronomy, geology, memory, music, and environmental observation into a single navigational technology. The astronomical aspect of this knowledge is particularly difficult to explain away as simple folklore. Many Aboriginal groups possessed highly detailed observations of the night sky. Seasonal changes, animal migrations, weather patterns, and ceremonial calendars were linked to the positions of stars in the Milky Way. The Southern Cross constellation was often used for orientation, while the appearance of specific stars marked environmental changes critical for survival. Several researchers studying Indigenous Australian astronomy noticed that some songlines mirror celestial pathways. Certain routes on Earth correspond symbolically to patterns in the sky, creating what some anthropologists describe as a dual navigation system, one terrestrial and one astronomical. At Chambers Pillar, this becomes especially intriguing because of the pillar's visibility and isolation. In flat desert terrain, a vertical landmark can function as a precise observational reference point. Some researchers believe formations like Chambers Pillar may have been used to monitor star risings, seasonal solar positions, and long-distance directional alignment. Unlike sites such as Stonehenge, there's no massive engineered observatory here. But that may be exactly why the knowledge remained underestimated for so long. Aboriginal astronomical systems relied less on monumental construction and more on environmental integration. The landscape itself became the instrument. Another mystery involves the petroglyphs and markings found around the region. Archaeological surveys have identified engravings and traces of repeated ceremonial use near Chambers Pillar, though many symbols remain difficult to interpret conclusively. Some geometric patterns resemble directional markers, while others appear connected to ritual pathways or cosmological stories. The difficulty lies in separating symbolic meaning from functional purpose. Modern researchers are increasingly recognizing that many ancient societies encoded practical survival information into mythology, ceremony, and art. In Australia, This may have allowed essential environmental knowledge to survive across thousands of years without written records. Some markings near the pillar are also positioned in areas that appear surprisingly difficult to access. Considering the fragile nature of sandstone surfaces, researchers still debate how ancient people repeatedly reached elevated positions without causing major structural collapse or erosion. But the most scientifically puzzling aspect of Chambers Pillar is not human at all. It is the pillar itself. The formation consists primarily of sandstone deposited during the Carboniferous period, roughly 350 million years ago. Over immense stretches of geological time, erosion stripped away most surrounding material, leaving the pillar standing in isolation. On paper, this should not be particularly unusual. Erosion regularly creates mesas, buttes, and rock columns throughout desert environments. What makes Chambers Pillar difficult to fully explain is its improbable durability. Sandstone is generally considered far less resistant than igneous rocks like granite or basalt. It is vulnerable to thermal stress, wind abrasion, water penetration, and granular disintegration. Yet Chambers Pillar has remained standing despite millions of years of exposure to extreme desert conditions. Temperatures in central Australia can fluctuate dramatically between day and night, producing continuous expansion and contraction inside the rock. Wind-driven sand acts like natural sand blasting equipment, slowly stripping away exposed surfaces grain by grain. During rare but intense rain events, water infiltrates fractures and accelerates weathering. Under such conditions, isolated sandstone structures should gradually weaken and collapse. Yet Chambers Pillar persists. Geologists believe several unusual factors may explain its survival. One theory involves differential cementation. Certain sections of the sandstone appear to contain stronger mineral bonding agents, possibly iron-rich compounds or silica cementation, making portions of the structure significantly harder than surrounding rock layers. Another possibility is aerodynamic erosion behavior. The pillar's shape may unintentionally reduce destructive turbulence around critical load-bearing zones. In other words, the structure may have evolved through erosion into a naturally stable geometry that slows its own destruction. Comparisons are often made to formations in Monument Valley in the United States, where isolated sandstone towers also survived long-term erosion. But Chambers Pillar exists under particularly severe thermal conditions, making its continued stability especially remarkable. Laser scanning studies of similar sandstone formations show that erosion does not occur evenly. Tiny differences in mineral density can dramatically alter survival times over millions of years. In some cases, a slightly harder internal layer can preserve an entire structure while surrounding landscapes disappear completely. Still, no geological model perfectly explains why Chambers Pillar remained so visually dominant while neighbouring formations eroded into near-flat desert. This has led some researchers to describe the pillar as a geological survivor anomaly. The mystery becomes even more compelling when combined with Aboriginal environmental knowledge. Ancient communities not only recognized the importance of Chambers Pillar, but integrated it into survival systems that lasted thousands of years without industrial technology. Modern desert survival relies heavily on GPS, satellite systems, engines, and digital maps. Yet Aboriginal Australians survived using observational intelligence alone. They tracked wind changes, memorized groundwater signs, understood seasonal star movements, and used geological formations as environmental data systems. Some anthropologists describe this as a form of ecological engineering, not through machines, but through cognitive adaptation. This challenges a major assumption of modern civilization, that advanced technology must always leave behind visible infrastructure. At Chambers Pillar, the technology may have existed almost entirely inside human memory. The deeper scientists investigate these ancient systems, the harder they become to dismiss as primitive. Unlike many ancient civilizations whose knowledge vanished with their monuments, this system survived for thousands of years through stories, songs, and the landscape itself. Surwa ancient city was discovered in the desert highlands west of Marib in Yemen, positioned along the ancient incense trade routes that once connected southern Arabia to the Mediterranean world. Archaeologists began major excavations in the 20th century, uncovering massive stone temples, fortified walls, hydraulic systems, and long inscriptions written in the ancient Sabaean Musnad script. What shocked researchers was not simply the age of the city, estimated at more than 2,500 years old, but the level of engineering hidden beneath one of the harshest environments on Earth. Annual rainfall in this region can fall below 100 millimeters. Temperatures regularly exceed 40 degrees Celsius, and yet Surwa once supported a stable urban population connected to one of the largest hydraulic civilizations in the ancient world. The first mystery surrounding Surwa is how such a complex stone city was constructed in an environment with almost no natural conditions favorable for large-scale architecture. Many of the surviving walls consist of enormous limestone and granite blocks weighing several tons each. Some joints between stones remain remarkably tight even after centuries of earthquakes, erosion and warfare. Unlike Roman construction, which often relied heavily on mortar and concrete, parts of Surwa appear to use carefully balanced dry stone techniques similar to those later seen in Inca sites such as Sacsayhuaman in Peru. Engineers studying ancient load distribution systems have noted that irregular polygonal stone fitting can absorb seismic stress more effectively than rigid uniform masonry. That raises a major question. How did the Sabaeans understand structural flexibility thousands of years before modern earthquake engineering? The transportation problem becomes even more difficult when examining the geography around Surwa. The surrounding terrain is rocky, mountainous, and extremely dry. There is little evidence for large forests capable of supplying massive wooden rollers or cranes, like those used in parts of ancient Rome. Some historians estimate that moving a single 10-ton stone block across desert terrain with primitive tools could require hundreds of labourers. Yet Surwa contains dozens of such stones positioned with surprising precision. Comparisons are often made to the construction mysteries of Petra in Jordan or the Nabatean desert fortresses, but Surwa predates many later Arabian engineering traditions. Even more puzzling is the lack of clear evidence showing exactly how the heaviest blocks were lifted and aligned. The greatest mystery of Surwa may be its relationship to water. The city stood near the legendary Marib Dam, one of the most ambitious hydraulic projects of the ancient world. Ancient sources and archaeological evidence suggest that the dam system irrigated thousands of hectares of farmland in one of the driest parts of Arabia. Some estimates suggest the broader irrigation network may have supported tens of thousands of people. Surwa appears to have functioned as part of this larger hydraulic system, possibly serving as a control center or regional distribution point. Archaeologists discovered channels, reservoirs, and stone-lined waterways near the city, many constructed with gradients so precise that water could travel long distances without destroying the channels through overflow or stagnation. Modern hydraulic engineers understand that even small errors in slope can destabilize irrigation systems, especially in arid climates where evaporation rates are extremely high. In Roman aqueduct systems, gradients often averaged only a few centimeters per 100 meters. Evidence from southern Arabia suggests the Sabaeans achieved similarly controlled water movement centuries before Roman hydraulic expansion reached its peak. This has created one of the most controversial debates surrounding Surwa. Did the Sabaeans independently develop advanced hydrological knowledge equal to or even surpassing some Mediterranean civilizations of the same era? Researchers have compared aspects of the Marib-Serwa irrigation network to Persian Qanat systems, Roman aqueducts, and Nabatean water harvesting systems at Petra. Yet Serwa's environment was arguably harsher than all of them. Maintaining long-term agriculture in such conditions would have required deep understanding of seasonal flooding, sediment control, evaporation management, and pressure distribution. Another mystery lies within the inscriptions carved into stone throughout Serwa. Some of the most famous inscriptions belong to King Karibil Watar, a ruler associated with military expansion and major construction projects. What makes these inscriptions unusual is that many appear administrative rather than purely religious. They reference campaigns, infrastructure, alliances, and dedications tied to large public works. Historians studying ancient state formation believe this indicates the Sabaeans possessed a surprisingly advanced bureaucratic system capable of organizing labor, managing resources, and maintaining regional infrastructure. This becomes even more significant when compared to other ancient civilizations. Large hydraulic systems historically required centralized administration. Ancient Egypt depended on Nile flood management. Mesopotamian cities relied on canal maintenance. The Roman Empire used extensive bureaucracies to sustain roads and aqueducts. Serwa suggests that southern Arabia may also have developed a sophisticated administrative engineering state that history has largely ignored. The city's temple structures introduce another unexplained layer. Several temples appear aligned with solar movements and seasonal cycles. While astronomical alignments are common in ancient architecture, researchers suspect the alignments at Serwa may have had practical environmental purposes. In desert societies, predicting seasonal rainfall and flood cycles could determine survival. Some scholars argue that astronomy in southern Arabia was not merely religious symbolism but part of environmental management. If true, Serwa represents a civilization where astronomy, engineering, agriculture, and political authority were deeply interconnected. The durability of the city itself remains another unresolved puzzle. Yemen experiences severe temperature fluctuations between day and night, conditions that gradually fracture stone through thermal expansion and contraction. Despite this, many Serwa structures survived for over 2 millennia. Some modern concrete structures in the region deteriorate faster than these ancient stone walls. Materials scientists studying ancient construction techniques have proposed that the specific stone selection, interlocking geometry, and stress distribution methods used by Sabaean builders created unusually resilient structures capable of surviving both seismic activity and extreme climate cycles. One particularly strange aspect is how little of the Sabaean technological tradition survived historically. Ancient Yemen once controlled the lucrative frankincense and myrrh trade, generating enormous wealth from routes extending toward the Mediterranean, East Africa, and possibly India. Serwa stood directly within this network, yet after the decline of the Marib Dam system, much of the civilization rapidly faded from power. Some historians believe repeated dam failures triggered agricultural collapse across the region. Others point to climate change, warfare, or shifting maritime trade routes that bypassed inland caravan cities. But the collapse itself raises disturbing parallels to modern civilization. Serwa appears to demonstrate how highly interconnected infrastructure systems can become catastrophically vulnerable when a central hydraulic network fails. If the irrigation systems collapsed, agriculture failed. If agriculture failed, trade routes weakened. If trade weakened, political authority fragmented. In that sense, Serwa may represent one of history's earliest examples of infrastructure dependency causing civilizational collapse. Do you think the Sabaeans truly developed engineering knowledge far beyond their time? Or are we still missing a major piece of the story behind Surwa? Share your thoughts in the comments below. Tamassos sat in the centre of Cyprus like a machine built for metal. Hidden between the Troodos copper belts and the trade routes of the eastern Mediterranean, the city became unimaginably wealthy more than 3,000 years ago. But the deeper archaeologists dug beneath Tamassos, the stranger it became. Underground mines with engineered airflow, smelting systems reaching temperatures above 1,200 degrees Celsius, royal tombs carved with impossible precision, and a vanished industrial civilization that may have controlled one of the ancient world's most important copper networks. The ruins of Tamassos were identified in the 19th century through inscriptions and classical references from Assyrian and Greek records. Major excavations later uncovered royal tombs, mining tunnels, furnaces, copper slag fields, hydraulic channels, and evidence of large-scale metallurgical production dating from the Cypro-Archaic and earlier Iron Age periods. Long before Rome dominated metal production, Cyprus was already one of the Mediterranean's primary copper suppliers. Ancient ships carried Cypriot copper ingots across Egypt, Anatolia, the Levant, and Greece. And some historians estimate that during parts of the Late Bronze Age, Cyprus may have produced a major percentage of the eastern Mediterranean's traded copper. Tamassos appears to have been one of the central engines behind that system. What makes the site mysterious is not simply the amount of copper extracted, but the engineering sophistication required to sustain production at that scale. Ancient mining around Tamassos was not random digging. Archaeologists discovered organized tunnel systems following ore veins with remarkable efficiency, and in several sections, shafts appear positioned to create natural convection airflow, where hot air rose upward through vertical openings, while cooler air entered lower tunnels, creating passive ventilation deep underground. The principle is strikingly similar to modern mine airflow engineering. Without electricity, mechanical fans, or modern geological mapping, the miners somehow identified ore-bearing zones with extraordinary accuracy. Excavation waste in some shafts is surprisingly low, suggesting they were not blindly searching for copper but already understood the geology beneath them. This becomes even more astonishing when compared to many later medieval mines, which often produced far larger amounts of discarded stone relative to usable ore. Some researchers believe generations of empirical knowledge allowed Cypriot miners to read subtle mineral discolorations, fractures, groundwater chemistry, and rock temperature changes with a level of observational skill modern people underestimate. The scale itself raises even more questions. Producing bronze required enormous quantities of copper, and a single Bronze Age trade network involving weapons, tools, armor, ritual objects, and ship fittings would have consumed thousands of tons over centuries. The slag heaps around Cyprus suggest industrial activity operating continuously for generations, while some estimates place ancient Cypriot copper production in the hundreds of thousands of tons over long periods of antiquity. That kind of sustained extraction required fuel, labor organization, transportation systems, and political control that rivaled early industrial economies. And yet Tamassos eventually vanished from global importance almost completely. The metallurgical remains at Tamassos are among the site's greatest mysteries. Copper smelting requires extremely high temperatures, and to separate copper from sulfide ores efficiently, ancient furnaces likely had to exceed 1,100 to 1,200 degrees Celsius. Reaching such temperatures consistently without modern refractory materials is difficult even for experimental archaeologists today, yet chemical analysis of slag from Cyprus shows evidence of highly efficient smelting. Some furnace remains indicate controlled oxygen flow systems, probably using tuyères connected to forced air bellows, while even more surprising is the evidence that furnace interiors were coated with heat-resistant clay mixtures capable of surviving repeated thermal stress. In several areas, vitrification inside furnace walls suggests prolonged exposure to extreme temperatures. Researchers have compared some Cypriot metallurgical sophistication to Hittite and Near Eastern industrial systems, but Tomassos still stands out because of the apparent scale concentration in one region. Even stranger is the alloy consistency. Several artifacts contain carefully balanced traces of arsenic and tin. Arsenical copper can significantly increase hardness, but controlling arsenic is dangerous because toxic fumes emerge during smelting. Yet, the metal composition in some objects remains remarkably stable, implying ancient metallurgists understood repeatable material ratios rather than relying entirely on accidental experimentation. That suggests something closer to proto-material science than primitive metallurgy. The royal tombs of Tomassos remained one of the most technically impressive features ever discovered on Cyprus. Buried underground, these tomb complexes contain stairways, chambers, pillars, and carved entrances shaped directly into limestone bedrock. Several walls display unusually flat surfaces and sharply cut angles inconsistent with rough quarry extraction. The precision becomes difficult to explain when considering the available tools of the era. Bronze tools are softer than stone, and although early iron tools existed, they were still limited. Yet some chamber interiors appear almost machine-finished under certain lighting conditions. Archaeologists believe abrasives such as quartz sand may have been used for prolonged polishing and smoothing. The tomb architecture also demonstrates advanced structural understanding. Cyprus sits in an active seismic region, and the island has experienced destructive earthquakes for millennia. Nevertheless, multiple underground chambers survived partially intact for over 2,000 years. Weight distribution inside the tombs appears deliberate, with load-bearing geometry reducing collapse risk. Modern engineers have noted similar principles in Mycenaean Tholos tombs and certain Egyptian subterranean chambers, though Tomassos developed its own regional style. Some entrances were once decorated with massive stone facades and sculptural elements influenced by both Phoenician and Greek traditions, showing that Tomassos stood at the crossroads of multiple civilizations. One of the least discussed but most fascinating mysteries at Tomassos involves water management. Mining operations require constant control of groundwater and runoff, and archaeologists identified channels and drainage systems cut directly through stone near industrial zones. Some maintain remarkably stable gradients over long distances. Even small slope miscalculations can stop water flow entirely or create destructive erosion, meaning that maintaining proper hydraulic angles without laser instruments or modern surveying tools required exceptional precision. Certain channels also include sediment traps resembling primitive filtration basins, suggesting the inhabitants were not only transporting water, but actively managing impurities and flow stability. Comparisons have been made with Persian Qanat systems and Roman hydraulic engineering, yet parts of the Tomassos network may predate some later Mediterranean water technologies traditionally considered more advanced. Excavations around Tomassos uncovered jewelry, ceremonial vessels, and decorative metal objects displaying extremely fine workmanship. Microscopic examinations of engraved patterns reveal highly controlled symmetry and repeated geometric spacing. Some gold and bronze ornaments contain lines so delicate that researchers still debate the exact engraving methods used. Pigments found on several artifacts present another mystery. Blue and green mineral-based colors derived from copper compounds survive for centuries despite exposure to oxidation and moisture. Similar long-lasting pigmentation appears in Egyptian faience and certain Roman mineral paints, but the preservation quality of some Cypriot examples remains exceptional. The combination of mining expertise, alloy control, pigment chemistry, and architectural engineering makes Tamassos appear less like an isolated ancient city and more like a specialized industrial knowledge center. Do you think Tamassos truly collapsed from environmental and economic decline, or could an entire ancient industrial knowledge system have been lost to history? Share your thoughts in the comments below.